talk on the engineering of materials by the ion beams.
Laser pointer is not working.
Okay, thank you, Mr. Ramila, for the kind introduction, and I hope this present. Battery. The slide is changed.
Slide change हो रहा है.
Okay, so thank you for your kind introduction. So good morning, everyone, and I will mainly talking about the engineering of materials by ion beams. And here I would like to give you the feeling that how we can use the energetic ions for manipulating the materials for various functionalities, including some of the fundamental interactions. So I have planned my talk in the following way. So first I will give you a brief look to the basically the kind of facilities there, because this is one of the inter-university center for making use of the facility by the university and the college teachers and the students. Then I will give a very brief introduction to that how such energetic ions interact with the materials, and they create some kind of the tracks, and tracks is having their own morphology for different applications, and what is the capability of such modified tracks for their functionalities. Then I will show some of the result, and let me see how much I will be able to complete. So I have chosen some of the examples that how one can use such energetic ions for manipulating the properties of the material. Finally, I will summarize. So this is one of the inter-university. There is no separate content. I will make it into also. If you have a stick also, I would be more comfortable. So this is one of the inter-university established by the university commission for the university people. So we have a vast research community all throughout the country and overseas. And we do have various research programs, like from the experimental physics, where I can do the reactions as well as the spectroscopy research. Then we do have a very vast program of material science, and we have a program of atomic and molecular physics, which is one of the very focused programs. Particularly, one can say the molecular kind of research. And then we have accelerated mass spectrometry program, where this is having a lot of application now in the building of the various antiquities, or you can say the archaeology. Now this has been taken as a new shape, that is basically known as the geochronology facility, where one can not only the researcher from the physics or you can say the environment science, but the people from the archaeology, history, geophysics, people can make use of the facility. Then we do have a very focused program of radiation biology, and there mainly we do study that how the cell can survive under the radiation condition, which is having a lot of relevance in the heterotherapy, like proton, or you can say the heavy ion therapy. And all these research programs is based on some of the other working accelerator facility at our place. The oldest, the 15 UD tandem photon accelerator, which is further boosted for the energy with the help of the superconducting linear accelerator. Then we do have an independent facility of 1.6 7 MB accelerator. It is mainly used for the elemental analysis using the RBS and the channeling studies. Then we do have one of the ECR based low energy ion beam facility. Mainly, you can say they manipulate the surface properties of the thin film, or one can say the nanostructure. One can think that one can modify the property in the near surface region with the help of the low energy beam available from this ECR based facility. Then we do have one positive ion facility, that is again one of the low energy facility, but mainly it is used for the implantation studies, where one can basically implant some of the active species inside some host or any other material for playing with the properties of the material. Then we do have you can say the ongoing development program, that is the drip tube LINAC. Drip tube LINAC is basically, you can say, it will again put the energy to, beam to the 15 unit, like in case of here in the superconducting linear accelerator, we are putting the beam from the electron accelerator. But now we can put the beam available from the drip tube LINAC accelerator, which is having basically much more higher current, which is very much required for the nuclear physics experiment. Then we do have a program of the 3 electron laser, where mainly essentially it could be used by the radiation biology and or the condensed physics people. And if you see the composition of the user base, so very vast community belongs to the material science program, then the nuclear physics, and then there are the other research program like the atomic molecular physics or the radiation biology. So here you can have a look to this. So this is our 15 UD tandem accelerator. So now this is the beam is put to these 3 superconducting linear accelerator modules to further boost the energy. And here now fine. Some of the slides is not supporting problem. So here, when the ions available from the accelerator, now they are interacting with the material and basically interacting with the material and transferring this energy to the material. So and the transfer of the energy will depend on the velocity of the incoming the ion beams. But if the velocity is very small, so essentially they are colliding with the atomic nuclei, because most of the mass is sitting in the nuclei, so they are having some kind of basically collision cascade, and that end up basically creating all kind of the defects, or even the complex defect structures. But if the velocity of the ions is equivalent to the orbital velocity of the electrons, so now they are started exchanging the energy with the electronic subsystem. Then there is a you can say the electron-electron relaxation process is there, but they are in the excited state. So finally, they dump energy to the lattice through the electron lattice or electron phonon coupling. So now there is, in a very short time, along a very narrow path of the ion, there is a spike. There is a drastic increase in the temperature. 2000 of the Kelvin temperature is confined to a very, very narrow zone. You can see these are basically the high resolution transmission electron micrographs. So this is basically confined, and that leads to the modification in the material along the path of these ions, and they have a different kind of morphology. Even if you can see here in this slide, so this is having some kind of the track region. Then there is some kind of the, you can say the periphery, you can have a different kind of structure. Then the remaining system remain as it is. So it is not affecting the remaining system. So that depends on how much the dose. How many number of ions should impact to the particular domain to modify the properties of the material. Whether you are interested in the single ion impact, that means you need to perform experiment at very low dose. And if you want to modify all throughout the thickness, that requires basically overlapping of such zones, so that it should be uniformly modified all throughout the area of your that particular material. And one can calculate that the temperature by solving these two coupled differential equations. That what was the lattice temperature during the spike process, which is essentially responsible for such kind of modifications. So here you can see that essentially the iron can be used for all kinds of process, whether they are the synthesis of the material. So these are the well-known techniques of the synthesis of the thin films or the nanostructure. We have some or other kind of the magnetic beams are involved, or whether it is the characterization of material. These are the very well-known. This is one facility that shown, and then the channeling again with the help of the same 1.7 MV accelerator, we can do the channeling. And channeling is one technique where not only the elemental composition of the material, but one can also analyze the crystallinity of your film, provided your films are the single crystals or they are the epitaxial thin films. Then ERDA is also one of the techniques where if you want to quantify the concentration of the lighter element all throughout the thickness of your film, with the help of this elastic recoil detection analysis, one can quantify that. With that, if there is even a variation in the concentration, we can do those studies. Then another technique is ion beam induced luminescence. Here, when this energetic ion is bombarding on the surface, particularly for the optoelectronic materials, there is the emission of the light. Mainly, I mean, one can say the visible or the near eye region. One can analyze this light and can know more about the materials, the kind of the effect creation dynamics into the material. Then if you see the tailoring or even modification or the functionalization of material, you can see in principle you can basically play with the whole class of the material. But as I pointed out in the beginning, because range of such energetic ions is limited to few micrometers. So all the modifications confined to the few micrometers only. And so whatever the active thin films which use, essentially they are the thickness of hundreds or 200 nanometer only. So these modifications are very uniform all throughout the thickness of the material here. So I will show some of the examples of particularly I will focus to the phase transformation and some example of the device that how they will respond when they are exposed to such energetic ions. So this is one such examples here. So here I will show that how one can basically start with a very highly crystalline phase of titanium dioxide with the rutile phase. That means the film is treated at a very high temperature, which lead to the very you can say the stable rutile phase, and how one can induce the nanocrystallization amorphous. Then you can further you can treat to the temperature and you can recover it back to the rutile phase. So I will show some such results in the next two slides here. So here, as you know. So here, like titanium dioxide, as everyone knows, that is having a lot of application in all kind of right from the photocatalysis to the photovoltaics here. But I will mainly focus about the phase transformation here. So you can see that at low temperature, it is stabilized in the anatase phase. When you treat to the higher temperature, it will transform to the rutile phase. And if you treat to the higher temperature and if you put the pressure, it can convert into the graphite phase here. So we have chosen mainly, it is having a lot of applications, so that's not here. Now, basically the issue with the titanium dioxide is related to the stability of their phases here. So their stability also depends on the size of the crystals here. So suppose the size is limited to the few nanometer, it remains stable in the anatase phase even up to the higher, but if the size grows, it transforms to the rutile phase. And if you control or you can inhibit the growth of the crystalline by some doping, like here in this case, we have doped with the niobium to inhibit the growth of the crystalline, it remains stable in the anatase phase even up to the higher temperature. So here I will just show some of such results here. So in this particular case, as I pointed of titanium dioxide and exposed to the 120 MeV silver ion, which deposited the energy of about 20.6 kiloelectron volt per nanometer in the nuclear excitation process. And then we did the in situ X-ray diffraction studies of this. So we are increasing the dose of the radiation, and on the same sample, we are taking the X-ray diffraction pattern after each dose of the irradiation. So you can see that how so here I am just zooming one particular reflection, that is 110 of the rutile phase. So how basically this particular material respond to the irradiation condition here. So if you do the analysis of this particular X-ray diffraction pattern by determining the size, that is constant, even you can figure intensity here, you can determine what will be the size of the dome created by each individual ion. So with the help of this, one can do. So here, with the help of this physical response, that is the formula, we can see that how each particular ion is modifying, what is the dimension of that domain which is modified by each individual ion. You can see here, even in this high resolution 10 micrographs, they are very highly crystalline system. We have with few, nanopeptides sitting in the amorphous oxide field. Now, from the same field, now we do the different experiments. Again, one of the in situ experiments. So we did the micro Raman during the radiation, again working on the single vessel with the help of the facility available here, and then we try to analyze it, basically respond to the modes of the micro Raman here. Then we do the analysis of the mode here. So you basically observe very large stability in this A1G mode. Here, when you do the analysis, so how one can basically understand this particular the process here. So we try to understand what will be the origin of a very large stability in this particular A1G mode here. So we try to understand this in terms of basically the bond order strength correlation mechanism here. So you can see here. So you can see here. So basically this apical the bonding basically that is getting modified, and that is responsible for the very large stability into this particular So now this film is completely amorphized, or you can say some having nanocrystalline phase. Now let's recover it back to the crystalline phase. So we will show the irreversible the transformation here. So now this is the starting with the amorphous film with some slides you can say sitting inside that amorphous background here. So now you are treating at different temperature. The same film is treating at different temperature. So you can say in very first course, but we are basically keeping the temperature same, and we are increasing the time only. Okay? To see basically how the growth of the slide is there, and then what we are doing basically here. So again we increase to the high temperature, and we are basically analyzing with the help of micro Raman etc. That what different kind of phases are there. So here now. Then we basically try to plot the integral intensity of the again the A1G. Okay, fine. So now basically we are plotting this intensity of E1 AG mode here, and this is the annealing time as pointed out here, and we try to understand what is basically the dynamics of the growth of the slides here. So basically in the beginning, mainly this is the very typical approach of three-dimensional growth of the crystal followed by the nucleus process here, and then after when you are, it is basically the nucleation is over. Now it is basically the growth which is happening at further timing, and then we try to understand that up to the critical radii of that particular crystal. After that, basically process tapering and growing to the higher band, and that basically leads to the phase transformation. But another interesting part here, then you treat this at high temperature. You can see here. So now I am increasing the temperature from because previously I was doing only the keeping the time same. Now we are increasing the temperature, keeping the time same here. And the same study also carried out with the help of the micro Raman study here. Now if you see the analysis, so you can see. So initially you can see this anatase phase is converted into the rutile, which is a conventional phase transformation here. But in this particular region, again, there is a transformation from the rutile phase to the anatase phase. This is basically region of the reversible phase transformation, which was not very well reported here. And after certain temperature, now again, there is basically again the typical growth from anatase phase to the rutile phase. This we also try to confirm from the soft X-ray measurements carried out at RADNET facility at Indore here, and also carried out micro to analyze the pattern. What is the phase structure is there? Whether really reversible phase transformation, so we confirm there is a reversible phase transformation in that particular domain here. Then we also try to determine the activation of this phase transformation. We confirm that yes, there is a reversible phase transformation. Then we propose the model that how basically when we started from 523 Kelvin, keeping the different timing, and how basically the overall growth is a control the dupletion followed by the growth, and finally the reversible phase transformation, and finally again, I mean this dissolution and precipitation control transformation to the required phase. Now the next study, what we do, we try to go with the niobium. So again, we inhibit the growth of the crystalline to remain, to keep it stable in the anatase phase here. You can see when we are doping at a different percentage of this is 5 atomic, percent here. You can see they will remain quite transparent and very good quality film without having the oxidation. We can also confirm the composition of the nitrogen with the help of the RPS technique, and by putting the gram simulation that what pressure of nitrogen is there in the lattice here. Then also we try to do the micrometer study. So here the films were treated at 2 different temperatures. So the one film is treated at 500 degrees centigrade, and 700 degrees centigrade here. You can see here, in case of the film which was treated at 500, there is not much change. Sorry, the film treated at the 500, there is a change in this particular V1G mode here. But the film which was treated at the 700, that basically, so what is the origin of this particular variation in this here? So that we try to understand basically how the coordination is affecting basically the position of this particular that we have also tried to understand what is the origin of whether the titanium remain in the 4 plus state, or it is basically reduced to 3 plus or 2 plus. That we confirm from the soft X-ray absorption measurements. So now here, the another important aspect when we are thinking of developing such a device based on such material, with one of the very crucial parameter is basically Fermi level. Is there any possibility to do the Fermi level with the help of the magnetic ions here? So here we have chosen 3 different kind of ions. 120 MeV silver ions, 130 MeV nickel ions, and 80 MeV oxygen. So when the energy deposited by the silver ions is more than certain threshold, which we have calculated in 15 kilolactane per nanometer here. So basically, then it gives to the very uniform modification all throughout the thickness of the film. But if it is around this value or below this value, then you have a discontinuous track, so you consider extended defects here. But if it is far below this particular threshold, basically essentially it induces some kind of point defects here. So how one can exploit these kind of energetic ions for playing with the Fermi level? So one can do this the direct measurement of scanning Kelvin probe microscopy here. So essentially where the measure the contact potential difference, and then finally one can convert it into the work function, or that you can basically convert it into the Fermi level here. And we have seen here that by doing the near age, or the soft X-ray absorption measurement at oxygen KL, that how the basically density of the states is changing near the conduction band here. So in this particular slide here, basically you can say normalize the deposited energy into the ion influence here. You can see here that as this value is increasing, you are able to basically tune the Fermi level. So with the help of such energetic ion, by choosing some particular parameter, one can play with the Fermi level of this material just by choosing the beam parameter. Now we have optimized the conditions, so can we develop a certain device out of this particular material? So again, the same nylon doped titanium dioxide film, which was N-type in nature. So we developed the type here. You can see here. So we try to see the composition of this with the RBS, then the microdrama, and also see the transmittance and the absorption. So the films are very nice. So now, when you do the photodiode measurement on this, you can see it is. So this is under the dark condition. So showing very nice the diode behavior, but when it was exposed to the light, the simulated solar light available from our solar simulator here, you can see there is a drastic reverse characteristic. This is essentially a characteristic of a photodiode. When you determine the various parameter of the photodiode, right from the contrast ratio at this particular voltage, which is reasonably very high, and also you can see there is a offset in the position that basically open circuit voltage, which is a 200 millivolt, essentially good for photovoltaic devices. And one can also determine the other diode parameter using the thermodynamic emission equation or the Chung equation. Now, the very interesting part is basically when you the important parameter for any photodiode is the responsivity of that diode here, and this, for this particular device comes out to 2.7 ampere per watt at 5 volt, which is very very high. And we try to understand the origin of what is the origin of this. And we have also developed the heterostructure diagram of the transport of the carrier across different regions, because there is a ohmic aluminum contact on the silicon. Then we have the NTO, that material. Then again the top contact of the silver. So one can basically understand the dynamics of the carrier under the dark condition and under the illumination condition. Now, question arises, when we use such diodes for radiation harsh application, what would be its response? So for that purpose, we carried out some experiment under 84 MeV silicon ions, and we carried out this in situ again during the irradiation itself. So what is the change in the IV response of this material? So here now there are two different regions here. One is just below the contact area, so only direct beam is not going to the active material. It is confined into the contacts here. So only the device is exposed to the secondary electrons here, and the outer region which is directly exposed to the radiation here. So here, so now as I pointed out, there are two different regions. How two different regions behave in a different manner. So but can determine the various diode parameters, as I pointed out, that after certain dose, that this identity factor, which is also one of the very important parameter, after certain dose there is an improvement followed by the degradation in this the parameter here. Then one can also determine the current density as well at the series resistance. That's how basically these parameters remain quite stable. One can also just by fitting this with the power law. So by determining the value of the exponent m, one can determine what is the origin of the transport of the carrier. So here, I mean, so you can say that you develop certain device, you play with the Fermi level, one can test the stability of such devices for possible radiation application. This is another example of the phase transformation. Here we have chosen the zirconia as interior here, and here you can see this exists in three different phases. At the room temperature, it is basically monoclinic phase, and you treat to the higher temperature, it converted into the tetragonal phase. But if you treat further at the higher temperature, it can convert it into the cubic phase here. So what would be its response when you expose to the irradiation here? So here you can see, so we have chosen two different kind of ions here. One is the nickel ions here, and this is the silver ions here. You can see when we are exposed to the nickel ions here, so this basically the doublet, this is the characteristic of the monoclinic phase of the zirconia here. So you can see here it remain there. Basically, then there is broadening, and finally there is basically the broadening of this particular phase. So partially there is a transformation to the tetragonic phase here. But when you do the same irradiation using the silver ions here, you can see it remains stable, and finally after that there is a two broad peak like in case of the nickel here, but beyond certain those now it is basically completely there is a new phase. That is basically characteristic peak of the tetragonic phase of the zirconia here, and even at the higher dose, there is a partial transformation from tetragonal to the cubic phase level, which we have confirmed from the extended age X-ray absorption fine structure study here. So essentially, one can say that by playing with the beam parameter, you can play with the phases, or you can say manipulate the phases of the material. Let me try to understand what is the origin of this particular, phase transformation here. Now the question arises, for such kind of phase transformation, how many minimum number of impacts are needed for the single zone to induce this complete phase transformation? For that purpose, we have carried out one the in situ experiment of again X-ray diffraction experiment here, then one in situ microremote experiment here, then by fitting the multiple ion model hit, that how many number of minimum impact is needed to basically transform one phase to the another phase. So we carried out from the either using the X-ray diffraction as well as from micro Raman, that how many minimum number of to be determined basically the 6 number of minimum impacts are needed to complete into phase transformation here. Then another basically of stabilizing the same cubic phase by doping the tria into the zirconia here. When you basically dope the tria into zirconia, it transforms into the stabilized cubic phase. Then we try to see the stability of this phase, it remains quite stable. And one can do the how you can induce the strain and how this strain basically because of the modification in the size of this particular material. So here I just like to summarize here that how the energetic ions can be used for the modification or manipulation properties of the materials, and very brief introduction that how energetic ions interact with the material, what are different kind of processes. So I missed some slide here. And then I have also shown that what are the capability of such energetic ions. Basically, ion-induced tracks, and the tracks is responsible for the modification of the properties of the material. Then I have chosen 2 different examples of the transformation material in the titanium dioxide as well as the zirconium dioxide. And I also try to show you the kinetics of the phase transformation. That means how many minimum number of impacts are needed for inducing certain. So thank you all, and I'm thankful to all the people involved in this, including Professor Rangasa. Thank you.
Thank you, Dr. Francis.
Sorry for initial hurdles in this slide.
That was okay. And I think now the paper is open for discussion, and we can have 1 or 2 questions. Or query? Anyone? Yes.
See, you talked about the local change in your ZRO2, and you also looked at the Fermi energy. See, my question is, there is a bulk Fermi energy, and because there is a local variation, your Fermi energies are going to be different when I do a Kelvin probe measurement.
The Fermi energy measurement basically we have carried out in the titanium dioxide films. Yes. Okay. So yes, you are right here, but basically here mainly we have carried out this work on the thickness, the characteristic value of Fermi energy more or less equal to the work Fermi value. That's what we have compared this value.
Any other question? If no question, let us thank the speaker with a big hand. Our next speaker is Professor S. Annapurni from Delhi University. So before inviting Professor Annapurni, let me have a brief introduction about her. Professor Annapurni has done a post-graduation from the Madurai Kamaraj University and then PhD from the IIT Chennai in 1990. Then she joined National Physical Laboratory in Delhi as a scientist, and she was there from 92 to 93. And later on, she joined Delhi University in 1993, and she's working as a professor, presently working as a professor at the Delhi University. And she has also developed a center for the nanotechnology in Delhi University, and she was also heading that center as a director of that center. And her field of study of research is magnetic materials, and the field she has published more than 160 research papers. So with this brief introduction, I'd like to invite Professor S. Annapurni to talk on the topic modeling magnetic switching behavior induced by thermal annealing and transient electron excitation of ion beams in magnetic multilayers. So please, Professor Annapurni.
Good morning, all of you all. Thanks a lot for this introduction. I should actually thank Professor Ramola. In fact, when we started our work at IUAC, he was my first collaborator, I would tell. Him and Dr. Subhash, with whom we did a lot of work. It was really very nice to work with this group. Very pleasant person, I would tell. And thanks a lot for giving this chance to talk to you all. Yeah, looking at what I saw, the seminars yesterday, this is going to be a completely. I think they should be able to hear it because we keep shouting. After listening to the talk yesterday, this is going to be a very different one. And first, I should thank Dr. Forensic because he has already given a lot of introduction on what can be done using the ion beam. Now, what I'm going to talk about is all of us talk about these magnetic materials where you use it as permanent magnets and as fridge magnets, or you also use it in magnetic memory. These days, with the digital world, what you want is you want a lot of storage that is needed. Now, is it possible for me to really look at the storage aspect of these magnetic materials? Is what I'm going to briefly look at. Okay, is right now whatever is existing with us as hard magnetic and hard storage material, is there a scope of further increasing? With that motivation, we started this work. So I'm just starting with this motivation of basic definition. If I have to look at a magnetic property, what are the basic parameters I need to look at? Then we also do a sort of a simulation where before going to the experiment, we would like to know, is there a possibility of any changes that you can expect from this? And I'm just showing 2 or 3 examples where we look at the annealing aspect. What I meant by annealing was, as we all know, as you have to go from a gas to a liquid to a solid, all that we need is a temperature. So I can use a temperature to get the phase transition. But another way of doing it is the local one, the ion beams, which he said, which can locally cause a phase transition, which is going to be more important if I'm going to look at a micro level or a nano level system. The ion beams are going to help me a lot in varying the parameters. So that is what I'm going to discuss. So let me start with the motivation here. If you look at the hard magnetic materials which are used in most of the magnetic memories, it is these alloy systems. What you call it as an iron platinum alloy, which has got a very, very, very strong phase transition. What I mean by phase transition in the case of magnetic material is whether it is an ordered material or a disordered material. Okay, you all know when I say ordered, sitting ordered in an orderly fashion or not sitting in an orderly fashion. And in the case of a magnetic material, it is basically the magnetic moment, the spin of the electrons which gets ordered. Whether these spins are going to be ordered or not is going to be whether my temperatures are high, temperatures are low. We all know that when you're going to heat water, initially it is remaining very inactive. But once you start heating, when it is reaching the boiling point, you see there's a bubbling is taking place. I would correlate these type of magnetic system to such a thing where I have electron spins which are remaining ordered. But once I start heating it, they become disordered, disoriented, which I do not want. I want a system which is perfectly ordered at room temperature. So if you look at the magnetic memory, this is what is happening. Yeah, this is the one. If you look at this, this is an iron platinum alloy, where if you see, these are small regions of alloy. This is a 30 nanometers. If you look at the scale, what I could see is that there are 4 particles within 30 nanometers. And if you look at what is going to be the memory level, is 9 terabytes per square inch is what you are seeing here. This is something which was done by Sun et al. 2000. This is what he showed. What we thought was, is it not possible for me to make these structures which are smaller than this? The reason being, every dot that I am showing is going to act as a memory, which means I can actually store information in each of these points. If it is possible for me to reduce the point, it is possible for me to increase the memory. So with that thing in mind, we did make it in our group, where we said that we can get around 36 terabytes per inch square. Now this is not the end of it. 36 terabyte per inch square is not a very high value. So what we want to look at is it possible for me to increase this? Now how do I do? Can I do a thermal variation, or can I look at an ion beam experiment to increase this aspect? So now, just to look at the geometry of the hard disk, it is just not enough for me to look at only the sizes. What is happening in these materials is, these materials are something called anisotropic in nature. What I mean by anisotropy is, whatever I see with a perpendicular may not be seen in a parallel one. So I have to look at, when I'm going to make a recording medium, see, if you see this is nothing but a south and the north pole, which we talk about in the case of a magnet. Whether I'm going to have an orientation along this parallel one, or is it going to be a perpendicular one, it is going to matter. So when I am going to make these materials for magnetic memory, I need to worry about whether there is going to be a parallel or a perpendicular anisotropy which is going to exist in this case. Now, how do you do? If I look at, this is what I have shown here, there is something called as a critical diameter. I said that reducing the diameter is going to increase the memory, but at the same time, I do have something as a critical diameter, which tells me that beyond a certain diameter, you might be thinking that I can store more information, but what you see is it goes to what is called as a superparamagnetic limit, which means I am thinking it is going to be magnetically stable, but I find when I make it smaller, it becomes unstable. The reason being, the temperature effect is so large that the spins of my electrons are not going to be ordered. But in my opinion, I thought that it will be ordered, but making the size smaller, we find it is not ordered because of a certain critical limit which makes it away from an ordered to a disordered limit. So what we need to investigate is there a possibility of increasing some other parameter, which even in spite of making it smaller, it will remain in the ferromagnetic regime. So what we call it as an effective anisotropy constant. And this is coming because of this perpendicular or a parallel way of looking at the system. So I am going to look at what are the two aspects we can look at. One is what I call it as a soft material. What is soft material is I can actually flip off the spin very easily. When I say there is an electronic spin which is present, there must be an external field which can act on it. For example, when I am changing my negative to a positive in a diode, you see that the direction of the current changes. Similarly, if I have a magnetic moment which is present, depending on the direction of the magnetic moment, what I can see is that I can flip the spin. So what I do here is, in this case, if you see, this is a soft material where I can flip off the spin fast, whereas this is a hard material where flipping is not possible. What I mean by hard is, these are the permanent magnets which we talk about. The permanent magnets are hard material, soft materials are the ones which you use in the transformer. So I need to worry about what is called as the hysteresis loop to basically understand what are the properties of these materials. So what is this magnetic hysteresis? I just would spend some time on that. So what happens is, given a magnetic material, I try to look at the response of the material to a magnetic field. If you see very clearly, slowly all my spins will get oriented in the direction of the magnetic field. But when I am going to reverse the field, I do not get back to this, which is what generally happens. In the case of an electrical circuit, when I switch on the voltages, there is a current which flows, I switch it off, it goes to a zero current. Whereas in the magnetic material, it doesn't happen. Initially what happens is your system follows the magnetic field, but later on it does not, what I call it as an hysteresis. The more the system is not going to listen to my magnetic field, I say it is an hard material, which essentially means that I need to have more of a reverse field to get back to its original position. Now, what is it that is happening inside the system? These are all very nice. I'll take a piece of iron and just put it in a magnet and try to do this. This is what I'm going to get. But what is happening inside? If I look at the inside of these materials, you have what is called as the domains. What it tells me is I cannot order all the electron spins to remain in the direction of the magnetic field. So there will be local regions where ordering takes place. So if I go to a high field, all of the magnetic movements are going to remain in that direction. So what next? Then what it tells me is there are two forces which are acting on it. One force which tells me that all my magnetic moments should remain in the same direction, which I call it as an exchange force. Because even without a magnetic field, all my magnetic moments are oriented. But then there is also something called as an anisotropy, which I said that depending on the direction of the magnetic field I give, it is going to change. So this decides the direction of spins. So this is what I have done. I simply taken a cubic system where I have shown these magnetic moment oriented here. But if I apply a field in three directions, what I will see is my system is not going to respond the same. So the same thing is going to happen if I take a magnetic memory. I assume that I have made a magnetic memory where I give a small field and I see that this is the response to the system. But unfortunately what I will see is if I am going to apply a field perpendicular to it or a field parallel to it, I will see that the system is going to respond in a two different ways. This is what I have indicated here. Now we do also a simulation where I said that within the magnetic domain, I am seeing that the magnetic moments of the spins are orienting itself. So we just did a small calculation. In fact, this is software which is available. I wouldn't go into all that. If you look at it very carefully, what you will see is if I take this as my material of 500 nanometers and divide them into small regions, what you will see is these are the spins which are randomly oriented. But when I apply a magnetic field, what happens is all these are oriented in a particular direction. This is something which, in fact, this is a free software for any student who want to learn it. It's a very good software which you can use, where you can look at the dynamics of domains by looking at how the domains are changing. So here we try to work out on a smooth film, which is an iron cobalt film, where we could see that at high magnetic field, all my magnetic moments are oriented in a direction. Now, this is not my only idea. The idea is I was telling that there is something called as an anisotropy, where I said if I change my direction, it is varying. So I use this to find out what I call it as an anisotropy constant, which is a very important parameter for me when I have to make the magnetic hard material or a soft material. So this is just to show you that at different fields, what is it happening? You can see very clearly at very small fields, we have a random orientation, and this is a domain where everything is in the same direction, smaller domain in the same direction. As I go to a high field, what you will see is all the domains are opened up and all the magnetic moments are in the same direction. Now, is this only an imagination for me? No, we can actually observe what we call as a magneto-optic microscopy, where I can really look at the domains. Here, the same material for which I did try to do the modeling, I try to look at the domains, or what is the possibility of the domains. You can see very clearly these black ones which are there, which essentially these are films which I am showing. The magnetic moments are in this direction, whereas the white ones which are here, which are in the opposite direction. So you can see this is the maximum field in which I have shown. One oriented in the direction of the magnetic field, the other one oriented opposite to the direction of the magnetic field. So what we have done is we only tried to establish this fact that we are able to see the domains in these films, but I literally want to see the domains, and we use a Mach microscopy to actually look at whether there is a possibility. If you look at it carefully here, I call it as a stripe domain. The reason is you have these stripes which are formed here. There can be several ways by which these domains can be formed. Now, it's not only looking at the domain structure. Another important aspect we did was these are very good antimicrobial agents is what we looked at. The reason being, these materials which can be formed, these materials which can be formed as a sort of a films, as forms of particles, if you look at it, they have very sharp edges. These sharp edges can tear apart the cell walls of most of these bacterial cells. So we use that aspect for looking at E. coli. We use an E. coli bacteria along with these iron cobalt system which has these sharp edges. Now you might ask me, is that what we saw? We found that if I'm going to use this E. coli, which we all know is an agent where it spoils your intestine. So what we try to look at is it possible for me to kill these E. coli bacteria using these materials? You might ask me why, how does it matter whether I use a material A or a material B to kill the bacteria? But what was interesting was, since these materials are very small, these are dynamic in nature. What I mean by dynamic is if I apply a magnetic field, there is a sort of rotational aspects which takes place. Now, because of these, which can tear my membranes, and if I can use these sharp edges near my E. coli bacteria, and there is a rotation which is taking place, you will see that it can very easily kill these bacteria. This is what we have shown. So with the field and without the field, we try to look at the E. coli, and then we could see that with such type of edges which we have, we can easily kill these bacteria, which we had one in a nanotechnology. This is one of the new things which we try to see, that if I'm going to change the strength of my magnetic field, is there any effect which is taking place? Yes, we did find that there is a cell death which took place very fast, and here is what we did with the field and without the magnetic field, depending on the amount of concentration of these nanoparticles which we use. So what we saw was not only looking at the aspect of a magnetic memory, in case if I can't use it as a magnetic memory, which I said that it's a superparamagnetic material, I can use it for these microorganism purpose. The second part we looked at is a simple system, because the iron platinum which I talked about is a bit of a complicated system which has got a phase transition. We try to look at a simple system. We all know cobalt is a metal which is present, which has got a very good phase transition. It can be in a face-centered cubic system, or it can be a hexagonal system. We want to look at what was happening when there is a thermal annealing and an ion beam. Because Professor Forensic said was, ion beams can change my system locally. Whereas when I do an annealing, it changes my system in a bulk way. So we wanted to look at it, and we had some interesting results on this. So how did we do? We did not want to do a simple cobalt. We want to have this cobalt embedded in a matrix. So what we did was we used an alumina. Alumina is a non-magnetic material. Cobalt is the magnetic one. And what you can see is we saw a very good phase transition, where when we did an annealing from 300 to 1100, where we could see that there is a transformation from an hexagonal to an FCC phase. We also tried to find it. So, which means you might ask me, in between there might be a phase where both can exist. Yes, we definitely saw that. So we have written the percentage of phases that can exist, and we did look at the system where there is perfectly 98% of my FCC phase. Now, what happened morphologically when I heat it? So I had an alumina. It is like having a little sheep between a big sheep flock which is there. So what we did was, when we put these cobalt and tried to heat them, these cobalt particles are very small in nature. And alumina is a matrix which is basically porous in nature. So when you heat it, you can see that this cobalt actually comes out. Because of the sizes which is smaller, there is a local heating, it takes place, it just boils and then comes and settles on the surface. That's what happens beyond that. If I'm going to heat it further, what you will see is all of them mixed together and it forms as a bigger particles here in this case. Similarly, the same thing happened, there was a local melting and after that it again breaks into smaller pieces. What I want to conclude from this morphology is that whatever was inside my system slowly came up after the boiling which took place. In fact, I'm not showing that. What happens is in many cases with the higher temperature, even they just evaporate off also from the top layer. Yeah, this is what I said, that it comes out of the surface through the alumina and evaporation and sublimation also takes place in the case of the cobalt system. So I try to look at what is happening at the hysteresis. Just now I told you that if I do an hysteresis in a different direction, there is going to be a variation. So we did it at a parallel and a perpendicular. What I meant by parallel and perpendicular is I have a film, apply a magnetic field perpendicular or apply it parallel to the film. If I look at it, these are the black and the red one shows that there is a difference when I do a parallel and a perpendicular, which for a person who is not working in this looks like simple graphs, but for me it's important because here in this case, if you see, this actually reaches a saturation fast and this has not reached my saturation. So this is something which I used to worry about because I would like, if I'm going to use it as a magnetic memory, I would like the saturation to be fast, which means I don't want to work with very high fields. I want very small fields at which I can saturate my system. So yeah, so what is it that is happening? See, I was telling in the memory part, there were two things which were important. One was the size and whether my phase is remaining the same. But the aspect that we did not look at is what will happen if I have a small impurity which is present in that. I think that I have made a material, excellent material with all sizes and all the properties that I need. But I actually look at the magnetic hysteresis, there is some flaw which comes in the hysteresis. A smooth hysteresis which I should get, I may not get it. What is the reason? I call what is called as pinning centers. It is basically, if we have all like a school, you have some all first standard kids standing there. Suddenly you are having some fifth standard kids standing. Similar to it, what happens here? So what is happening is I have a cobalt system which is present. In between there is something else which is there. So when I'm going to apply a magnetic field, this guy is not going to keep quiet. He is going to show it in my hysteresis. So this is what I'm demonstrating here. If I'm going to have a very small impurity which is other than my cobalt, what I will see is at field h equal to 0, nothing is going to be seen. But if I keep on increasing my field, what I said was there are small domains which are present. These starts growing. But this small fellow is not allowing the growth of my domains, which essentially means my hysteresis is not going to be smooth. Earlier, if you saw that, I had a very smooth hysteresis, which I have shown. But if I'm going to have such a system, I will not see a smooth hysteresis. This is one aspect which is important for me when I'm going to do a magnetic memory. I do not want that even one atom, which is an impurity atom which is present, which is going to spoil whole of my magnetic memory which is present. So this is what I have demonstrated. What is it that is happening when there is a growth? This is not allowing my growth of my domain. So I do not want such a system in this case. Now, looking at what I call it as a pinning and a depinning. What do I mean by a pinning is, it is like on a board, on a free board which is present, I just put a pin, which is not allowing for me to do a drawing. Similar to it, if I have this impurity, which I call it as a pinning center, is not allowing my hysteresis to grow properly. So what we did was, we thought, if suppose instead of doing a thermal annealing, if I'm going to do an ion beam, can it help me? This is what we looked at. What you can see is the same thing was happening in this case. In the case of thermal annealing, I saw smaller particles coming up, whereas here, ion beam, as Singh was telling, ion beam are good enough that it does a local heating in the sample. So when there is a local heating, again, this cobalt actually comes out on the surface, and what you see is the cobalt actually grows. You look at it, this is 2 microns. So for me, my ion beam was not a good thing at all. Sorry to Professor Forensic. For me, it didn't work out well. Yeah, the annealing aspect was better for me in this case. So what we used was not it's a argon 300 kV. Maybe we need to change the fluences or the energy of the argon to get what we saw in the other case. So yeah, if you look at the magnetic hysteresis are not much different at all. So that way it is fine. As far as the bulk properties are concerned, it did a good job. But as far as morphology was concerned, it was not a good job at all. Yeah. So what we did was, I told you that if I am going to give a magnetic field parallel and perpendicular, I am going to see a variation in the hysteresis. But what I can find out is there a gradual change or is a sudden change? How do I do? I apply the magnetic field at different direction, not only perpendicular and parallel, at every 1 degree of magnetic field. I'm going to look at what is happening. What you have is something called as a polar graph here. This is a perfect graph. This tells me that either my anisotropy is along the perpendicular field or it is parallel to my film direction. But as I changed it by the ion, I found that there is a variation, which is not a bad aspect at all. If I try to look at the morphology, I was not happy about it. But if I try to look at this aspect of this variation, what it tells me is I need not worry about whether I have to do parallel or perpendicular. What I will see is mostly in all directions, I'm seeing there is an isotropy. So magnetically, what I see with the ion beam, there is an isotropy, which I did not see in the case of my thermal energy. So this was one positive aspect which I looked at with the ion. So we also did the Monte Carlo simulation. Let me not get into again the way we did the simulation there, because I want to be very sure whatever graph I'm getting is an appropriate graph or not. We try to do some calculation. We use either a Python or a Fortran in this case, where we look at what are the different aspects and find the parameters which are necessary for me, so that when I'm doing my next experiment, I can be more careful of what has to be done. So another system which I look at is the strain that is induced. In one aspect, we looked at the sizes are becoming smaller and the material is just melting and coming to the surface. But here, I'm looking at a system where no melting, nothing takes place, but it causes a strain. What do I mean by a strain? You just take a matchbox where you try to push in all your matchsticks. You know, if you start pushing more matchsticks into it, it strains my next matchsticks. This is what is happening. So I have a unit cell which is present, which says that my atoms have to be in this place, but I'm going to push something in between. What happens is it strains my lattice. So this is what I said, that engineering strain is I purposely induce a strain and try to look at what is happening to the magnetic properties. This again, iron platinum which I talked about is again the material which can be used for magnetic memory. So here in this case we used a swift heavy ion. We looked at both oxygen as well as Ag. What we found was the aim was to calculate, if I have given the thick of a film, what should be the energy that is needed so that it will completely go through my film, or what is the place that will stop, which it stops. It will be interesting when we look at it later. Yeah. What we found was when we use these dense excitation with the oxygen, so in fact we try to look at the XRD, which is one particular plane 100. After my excitation, what I could see is there is a shift. This is what I call as a spin. So what has happened is, by these ion beams which I put in, I found that there is a straining in my lattice which has taken place. Now what has happened? It has increased my order parameter. The idea is I want an ordering in my film. I don't want my films to be disordered. If it is disordered, I just keep it aside. I want an ordered film. What we found was that the ordering parameter actually increased in the case of ion beam. The earlier I said my ordering was not good, but magnetically it did sound very well. But here in this case, even structurally, I could see there is a good ordering that was taking place. Now, what did happen? Now, what we found was there was a sort of a densification in my material which took place. As a result of this, look at the history. This I'm having a very broad hysteresis. Earlier I showed a hysteresis which was very thin. Now I have a very broad hysteresis, which actually shows me that there is a phase transition going from a softer to a harder phase, and harder phase is very high. In fact, I have 1 Tesla, which is here, which essentially tells me these are excellent materials for using as magnet or for magnetic memory. Okay? So I just compared the annealing as well as the order parameter. If you see, the annealing, the order parameter was only 0.9, whereas with iron beam we found that the order parameter is large for me. I just leave the filling. Just look at the last one. Now, initially we talked about a cobalt which was put in an aluminum matrix. The other one I tried to look at iron platinum. But here what I do is I simply use the platinum, cobalt and platinum. Is it possible for me to use the iron beam to locally melt it and form as an alloy? Initially I started with an alloy. Here I start with individual metals and I want to see whether alloying can take place. So we did a platinum, cobalt, platinum, which again is used for magnetic memory. So what we found was that when we did the sputtering and when we did the annealing, let me show the annealing part. So this is what we can see. So this is looking at the electron image where we are seeing the amount of cobalt. Yeah, the composition, if you see, it is CO44 and PT56. I started with a simple metal. After my annealing as well as my iron beam, I found that there is a sort of nice mixing which is taking place, which we compared by looking at the electron image, and we could look at what is the composition. Yeah, in fact, the RBS which he used is using the iron beam, where you can find out. Look at this. The platinum layers are very clear before I anneal it, when I just deposited the film. But later on, if you see, they all diffuse itself to form a nice alloy. Okay? So this is what we did with the iron beam, and what we found was that using the O7 plus and 8015, what we could see is that there is nice variation in the magnetic hysteresis loop. So I will conclude here by saying that your grain growth can be controlled both by thermal annealing as well as by your iron beam irradiation. And here in this case, I need not look at the phase transition. I can simply engineer my strain in the system to get the best magnetic properties. And third part is what we found was, if I can combine thermal as well as the iron beam, I get the maximum utility of this system. So with that, I think I should thank all my funding agencies and my collaborators and my students, without whom all this work would not have been done definitely. So these are my students working in different areas. Thanks a lot.
Thank you for this impressive and informative talk. And now I think we can have 2 questions. The talk is now open for the discussion. Any question? Yeah, Professor Bhajan.
Sorry, I went slightly late. I couldn't go through all of the presentation.
Yeah.
It's quite informative, I think so. So it means the incoming ion beam flux,
Yes.
the high intensity ion beam flux,
Yes.
plus the thermal annealing,
Yeah.
that will lead to a good structure which can be used for multivariate.
Exactly. See, especially nowadays, what they do is, rather than simply putting the iron beam, they put a mask.
Okay.
Okay, they put a mask so that locally several areas, I can do, so that that particular small spot will become a magnetic memory area.
So that we can even pinpoint to the areas
Yes.
where we want to increase
Yes,
the strength.
exactly. So see, sometimes what I may need is, I may need a soft as well a hard material. So suppose I make a hard material and I put a mask and I put the iron beam, only those regions where iron, because as he showed, it doesn't go.
Yeah, you can control the strain.
Yes, I can.
Where you want to have.
Yes.
That's a beautiful. One thing I was interested when you're putting a high energy ion beam flux
Yes.
for doing this nice job. So, is there any, as you plotted the ion beam energy loss versus the energy itself?
Yes.
Of course, it's going to decrease.
Yes.
Yeah.
Yeah.
But What about the case of, because we are giving a very high ion beam
High
flux?
fluence is
What-
something which
What
I
about the
don't
energy
want.
which is given in terms of maybe some bremsstrahlung radiation which are coming up, or maybe in terms of some,
See, in fact, we need to do a lot of studies on that to really pinpoint what you're asking.
To the-
Because here, what I need to do then is I have to change my energies, I have to change the fluence also. So I have to exactly find out which energy, which ion. Of course, that is
energy loss
going.
because of those radiation not taken into consideration.
Yes, and also my density of the system which I'm studying. If I use a alumina and a cobalt system, it is different. But if I use an iron platinum, it will be different. So that's.
Anyway, it is quite informative.
Thanks, sir.
Any other question? Yeah, there's one more question, please.
Yes.
Sorry, I would like to ask something about the iron oxide particles.
Yes.
People in your laboratory?
Yes.
Because only due to the cancer traffic is
Yes, yes.
very
We
useful.
do iron oxide also we prepare. Though we prepare iron cobalt also. Because iron oxide, the response to magnetic field is not very good. But iron cobalt is very good because it's a very soft material with a high magnetic moment which is present.
And did you try in the cancer therapy? No.
Because we don't have any collaboration with the medical centers. So
Okay, maybe I
for
will-
that we need a.
I will try to
Yeah,
fancy
yeah.
check.
Chairperson or assistant professor to present a memento to invite the speaker of the policy as a again I guess Professor Amola sir to present memento to Professor Anil Polina.
Your introduction to IUSC, I would tell you.
So, thank you, sir. Now, in the world presentation, in the series of world presentation, the first speaker is Subhash Chandra, and he will talk on effect on band gap and digital activities on energetic and related polyol thin films. So, please.
Good morning to all. The topic of my presentation is effect on bandgap and DC conductivity of energetic ion irradiated polypyrrole. Polymers are known to have good insulating property, but by doping, we can vary the conductivity of these conducting polymers from insulating regime to conducting regime. And with the inflection of ion, we can alter all the properties like optical, electrical, and mechanical properties, and some defects can be found on the polymers. This is comparison of conducting polymers with conventional conductors. The conductivity can be changed from 10 to the power minus 10 to 10 to the power 5 from insulator to metal regime. And these are some overviews and potential applications of polymers. Can be used in molecular electronics, can be used in some devices like resonance, tunneling diodes, optical computers, LED, solar cells, and some other units. The polypyrrole square synthesized by electrochemical method by using the monomer of paratoluene sulfuric acid and their W square synthesized by the oxidation process by the electrolytic method. Ion beam infection. The conducting polymers can be modified. The property of these can be modified by using the ion beams. Some new bonds may form by bonds addition, cross-linking, and the trilations, X-ray diffraction. From this study, we can study the amorphous or crystallization nature of these polymers. This is the XRD pattern, and this is for the pure polyvinyl films. And after relation with the nickel beam of energy 120 MeV, the crystallinity of these films were found improved. From this, the crystallinity was calculated, the crystallite size was calculated from the Serres formula. The different places of the nickel beam were used, and then it was found that after interaction with the swift gas, the crystallinity of these films was found increased, and the crystallite size was found varies from different sizes. UV spectroscopy. By this study, we can find the change in the band gap due to the unusual production of electron hole pairs after heavy ion radiation and the transition loss in the materials. This is the UV study, and it was found that there is slight change in the spectroscopy of these fields, and from this the band gap was calculated and found that initially the 3.5 electron volt band gap was for the crystal sample, and then it was decreases after relation with the various places, and it was decreases up to 2.9 electron volt. And these are light in band gap. These are the conductivity measurements. IV characteristics. It was done by using the four-probe method, and these are the IV measurements of the polyvinyl films, and it was found that the conductivity was increased. For the crystalline films, it was found that 40 Siemens per centimeter, and after relation with different places, it was found increased, which is good match with the XRD and the UV visible spectroscopy. And the increase in the conductivity is maybe due to the formation of the polarance and bipolarance, which moves along the polymer chain by hopping mechanism, and therefore it increases the conductivity of the polymers. This is the low temperature conductivity measurement for the polyvinyl films. It was found that initially it shows the semiconductor behavior, but at low temperature it shows the metallic behavior, and it is a good match with our IV measurements and XRD some other measurements. This is plots for the conducting with the temperature, and this is the time fitting shows the metallic behavior of these. Conclusions. Polycarbonate films were synthesized successfully. The band gap reduces after the invasion, and at higher temperatures, some bonds are seen to be shifting towards a higher wave number, indicating that the irradiated polyvinyl films contain shorter conjugated chains as compared to the pristine polyvinyl films. The room temperature conductivity increases after radiation, which may be due to formation of some new bonds or polarance and bipolarance, and after radiation at low temperature it shows the metallic behavior after radiation. Thank you.
Okay, very open for discussion.
High flux irradiation, what is the conductivity? 10 to the power 12. Table shows almost why 10 to the power of 11 105. 10 to the power of 12 flex there is no.
There was no measurement.
It was burned
It
actually.
must have burned.
Not available, not available.
Yeah, one more.
Subhash, I have a very basic question. You are talking about basically direct and indirect band gap. As such, in conducting polymer, basically there is a LUMO-HOMO transitions is there. Right? So as such, there is no dispersion like in semiconductors or any material. In this case, so what do we mean direct or indirect band gap semiconductors here? Band gap, you mentioned. You are getting my point. Huh? In semiconductors or any material, there is a dispersion. Okay. So whether it is a direct band gap or whether it is a indirect band gap, you can define. But in case of conducting polymer, basically this is the LUMO-HOMO transitions is there, right? So you can say some kind of direct band gap, but what is meaning of the indirect band gap here?
Actually, polymer it is not defined actually.
Yeah. Okay.
Okay, thank you, Subhash. So, next, it is N.T. Mandlik, and he will present his paper on luminescence studies of European doped Y2O3 nano homosphere synthesized by Soldier method. Okay.
Good morning to all of you. I am presenting the paper Luminescence Studies of European Dope lithium oxide nanophosphor synthesized by the Soldier method.
Left and right.
Slides. Radiation dosimetry. European dope lithium oxide nanophosphor is used for radiation dosimetry purposes also. Now, if you do the sample for the radiation dosimetry, it has some characteristics, ideal characteristics. It should have low feeding. Its thermoluminescence peak should be at high temperature. Then excellent reusability. Then wide and linear dose response. And also high intensity or high sensitivity. This nanophosphor is synthesized by the Soldier method. Yttrium oxide and European fluoride in the appropriate ratio. Initially, it is taken European fluoride as 0.2 moles. They are mixed in a distilled water, stirred. There is some few drops. Now, the high humidity solution will occur, and some few drops of HNO3 will added in it to dissolve it completely. Then heated at 100 degrees centigrade around 2 hours. The Milky Way solution turned into a viscous transport solution. Then citric acid is added in the molar ratio of 2:1, and the pH of the solution is maintained at 1. The solution then heated at 90 degrees centigrade slowly up to 8 to 10 hours, and the pale yellow color J was formed, and as shown in this figure, here first figure. The J was heated at a slow heating rate of 2 degrees centigrade per minute at 800 degrees centigrade for 2 hours in a tubular furnace. Then a white fluffy mass was formed in the aluminum board. Then the powder is crushed, and this is crushed and powder is formed. And again, this powder is annealed for high temperature of 800 degrees centigrade for 2 hours, 1600 degrees centigrade for 2 hours, and again slowly cooled to room temperature. Similar process is followed for the higher doping concentrations, 0.2 mole to 20 mole percent. This is structural analysis. The phase formed in the cubic structure, and the lattice constants that constant is around 10.60 and it is in it is nearly equal to the JCPDS data. The samples I need from 800 degrees centigrade to 1600 degrees centigrade is shown in the first figure. And again, the sample is optimized because we get the thermoluminescence intensity maximum at 1600 degrees centigrade. So sample synthesized by different molar concentration annually at 1600 degrees centigrade, and again XRD is taken from 0 mole percent to the 10 mole percent, and again 21 percent also, and all in the cubic phase. Here, europium and etherium have similar ionic radiuses, around similar ionic radius. So the etherium atom was replaced by the europium atom. The morphological analysis. So these few figures these are the FESM figures. Now, figure A is for the as synthesized sample. That means if the sample is annealed in a tube at 800 degrees, J is annealed in a tube. Tubular flow is 800 degrees centigrade, and then again it is annealed at different temperatures. Here B figure shows the annealed at 1200 degrees centigrade, and the third figure shows the 1600 degrees centigrade. Again, if EM images are taken and D, F, and E and G, these images shown on the EM images, it shows the particle size around 20 to 40 nanometer. If it is annealed at high temperature, of course there is agglomeration, and in as shown in figure C, the particles grow of a larger size, and ACD pattern also shown, and interspacing distance corresponding to Kutu plane, because growth of the Kutu plane is higher in XRD, it is 0.305 nanometer. And ACD pattern shows clear bright diffraction patterns demonstrating the polycrystalline nature of etherium oxide. And ACD analysis is in matches with the XRD peaks. Composition analysis, EDAX is taken, and EDAX it shows the composition of etherium, oxygen, and also small amount of europium also, because europium is looked in the ppm level. Presence of these peaks shown in the diagram of EU, one at around 1.1 kV and another at around 5.8 kV. X-ray photoelectron spectroscopy also taken in support of this all the document. Now here this one sample is sample annual at 800 degrees centigrade, 0 mole, unload sample, then 800 degrees centigrade, 1 mole, then 1 mole sample annual at 1200 degrees centigrade, 1 mole sample annual at 1600 degrees centigrade. And these samples consist of the peaks of Y4P, Y3D, Y3P, and Y3S. And also oxygen is identified by O1S peak and OKLL peak. And it is a confirmation that there is a formation of etherium oxide, and also there is a less doping of EU. So EU peaks are not clearly seen, but with the decapitated electron we can see. And EU peak is not clearly seen, but the positions are at 1126 and 1155 electron volt. And also there is a carbon peak shown, because in HPS general carbon peak we can see. And here we anneal it in the atmosphere, in air. The sample we anneal in the air atmosphere. So CO, because of there will be CO2 and some carbon peaks are also present here. These are the XPS deconvoluted here in this Y3D. It is the sample and 1600 degrees centigrade, 1 mole sample. Now Y3D peak show the distinct spin orbital doublet 3D 5 by 2 and 3D 3 by 2, and the lower binding state 3 5 by 2 assigned to YO bond, and the binding state assigned higher binding state YOH assigned to this YOH, and indicate the presence of Y2O3. Also in the next diagram, then C diagram, also there is a presence of the deconvolution of O1S peak of the as synthesized etherium oxide, and have two prominent peaks again, and there is a YOH and YO bond existing in Y2O3. It shows that there is a presence of some hydroxyl sites corresponding to this 532. Now deconvolution of O1S peak for the sample annual 1600 degrees centigrade, here in the B figure. again shows the existence of YOH and YO bonds, and also an additional peak of OU, small peak, was observed at 530.85 electron volt, which was not observed in undoped sample. That means in the figure C, indicating the presence of europium in the sample bonded with the oxygen bonds. So this is the confirmation that europium is doped in the sample. In optical analysis, we had analyzed the sample at different temperature. We have doped the sample from 0 mole percent to 0.2 mole percent to 20 mole percent, and the samples are annealed at 1600 degrees centigrade. Now, in this figure A, we can see the sample, of course, it is in white in nature, and if it is, it gives the red color under the UV light. And in this figure C, shows the changing color of the sample under UV illumination of different mode. And you can see that its radiance increases with the molarity, and 20 mole sample gives the intense red color, and Ethereum oxide doped with the europium, it is a red phosphorus. So again, it is confirmation with the photoluminescence study. The first figure is the excitation spectra at emission at 612, and figure B is the emission spectra at excitation of 261 nanometer. And 612 figure is it is in the red region, and it is an intense peak showing that it is a red phosphorus. Also, here this is the 20 mole sample. Now, we have taken the PL emission spectra of the samples of different mole. Here 1 mole and 20 mole is shown, and you can see the 1 mole sample having the less intensity, but 20 mole sample given the intense peak of 612, and you can see a confirmation that in 20 mole here, this 20 mole gives the reddish color, more red color. Now, CI chromatocity diagram. Again, the CI coordinates were observed to vary with varying doping concentrations and annealing temperature. The first graph is for the 1 mole sample annealed at different temperature. That means graph of all. That means 1 mole annealed at 800 to 1600 degrees centigrade. CI is taken. All graph are combined in one graph, and same for the 20 mole in the graph B. The reddish orange color in the first graph, the reddish orange color emitted by the 1 mole and phosphor is mainly useful in orange strip lines, then candle lighting. And you can see there is orange red color, and in second figure we get a deep red color. So color purity of 20 mole sample doped with European phosphor is higher than the 1 mole sample. Here in this you can see the color purity is around 72% in case of 1 mole sample, and color purity is around 96% or 98% in 20 mole sample. So, color purity, if you prepare white LED, so RGB colors are important, red, green, and blue. So here the red phosphor can be used for white light emitting diodes. Now thermoluminescence studies. Here is the first figure, clear glow curve of 1 mole doped sample for different annealing color, different sample annealed at different temperatures, and in the figure B, it shows total intensity versus annealing temperature. And 1600 degree sample gives the maximum PL intensity. In C and D, the sample annealed at 16 degrees centigrade of different mode, this clear glow curve are plot, and in figure B, it shows the sample 20 mole sample has the maximum PL intensity, and the optimized sample is related with the different doses from 120 grade to 100 kilo grade, and it shows the linear response up to 1 kilo grade, and then from 100 kilo grade it shows the sublinear response. So this sample can be used for the food irradiation also, and this feeding and usability. It is observed that the feeding is much higher in the first 5 days, because the first peak is at 100 degrees centigrade, and it is fed within very few days. So after 5 days, the sample can be used for the dosimetry purposes, and it has a good usability. And here deconvolution of the sample is Tmax is stopped with the reduced final condition. Yes. And this first peak is within the 2 days. And this is the conclusion that this is a good red phosphor and it can be used for the high dose for the dosimetry purposes such as dosing. Thank you.
Thank you. Now, yes, please.
Your thing is 20 mole percentage, but at 20 mole percentage is supposed to show some self-quenching effect actually. Because of europium interaction, there will be basically cross relaxation processes will start happening.
Intensity case.
Yeah,
So
intensity,
TL intensity.
TL intensity.
But this XPS doesn't show European, no?
Madam, this is for I think 1 mole. We'll take the 20 mole sample. It's just for 20 mole sample. It is for 1 mole. It doesn't show the European. European is around 1126. There are some very small peaks, but cannot be identified here.
Did you do ESR or something?
Yes, sir.
ESR
Maybe
can tell
should.
you. Yeah.
But here one small peak of OU you can see here in decolonization.
Because you need to reconfirm whether it is 20 mole percentage really it is a 20 mole percent into your matrix or not. Okay.
Thank you, sir. Thank you, Professor Mandle.
Thank you.
Now, the next speaker is Dilip Mina. So, and he will talk about wedge solidification rate dependent structural and thermoelectric properties of sp2-TgT nano composites.
Good morning, everyone. My name is Dilip. I'm assistant professor in SRT campus, HNCGU. Today I will talk about the mass modification rate dependent structural and thermoelectric properties of sp2-TE3 TE nanocomposite. This work has been done in the ISC Bangalore. So first I will give the basic introduction of thermoelectric materials. Then I will tell the how to prepare my sample, the microstructural properties, the thermoelectric properties, and finally I will summarize my talk. So by the survey, whatever energy we are producing in the whole world by the primary energy sources like thermal power plant, nuclear power plant, and etc. 56% energy is waste as a waste energy, and only 34% energy we can able to use as a usable energy. So by the use of thermoelectric, we can convert this waste heat into the electrical energy, and by changing the thermal energy to electrical energy and vice versa is called the thermoelectric. These are some applications of the thermoelectric materials. So in the first one, waste heat we are converting to the charging electricity, and we are using that electricity to charging the mobile. And in second one, by the exhaust of the car, we are taking this waste heat and using in the electricity of this car. And the other applications are, these are two other applications which are on the basis of the Peltier effect. These are some three basic phenomena of the thermoelectric effect: Seebeck effect, Peltier effect, and Thomson effect. Seebeck effect is nothing but if we take the two dissimilar materials and if we give the temperature gradient there, then some voltage difference will generate, and this Seebeck coefficient is given by S is equals to limit delta T tends to 0, delta V by delta T. The Peltier effect, if we take two dissimilar materials and if we flow some current through it, the circuit, then on the one junction the heat will liberate, and other junction the heat will absorb through the junction. Third one is the Thomson effect. Thomson effect, if we take a single material, if we pass some current through it, either the heat will liberate or eject from the material. For the practical use, we need the thermoelectric generator. So for making a thermoelectric generator, we need a batch P-type material and batch N-type material. And if we take this type of units and combine these in the thermally parallel electrical series, then we can make a thermoelectric generator. So the figure of merit of a thermoelectric generator is given by that is equal to S square sigma from kappa into T. And these all the factors are depending on the carrier concentration and the mobility of the material. So for taking the good sulfuric materials, we need to take the current concentration between 10 to the power 19 to 10 to the power 20. That is for the semiconductor materials. So the best semiconductor materials are the best conducting materials also. So for my sample, I took these are the best conducting materials presented in this slide. So for the practical use, I took nearby the room temperature Sp2Te3 because we need a best P-type or best N-type material to make a conducting generator. So Sp2Te3 is the best P-type material, conducting material for the room temperature. So this is the synthesis method. We take the Sp and tellurium powder and then we grind it and put in the coil tube with a high vacuum pressure for -6 millibar. Then we reach to the temperature for 1073 kelvins. For 10 hours we wait there and we quench with the different quenching mediums. Alkali water, ice water, normal water, liquid nitrogen and air quenching. And we finally got the 5 ingots. When these 5 ingots we use as a 5 different samples. So this is the XRD of the ingot. So all the 5 XRDs are shown here for the different quenching mediums. So 015 peak, I am showing in the figure G. There is some variation in 015 peak, the 2 theta values. It is showing there is some defect is present inside the material for different samples for different quenching mediums. This is the radial refinement which we have done by the foolproof method. And we, by the help of this radial refinement, we calculated the parameters, status parameters of the samples. This is the thermal TGA analysis. In TGA analysis, we are seeing that there is 2 endosonic peaks we are getting at the 700 Kelvin and 900 Kelvin. So these are the presents that there is tellurium and Sp2Te3, 2 different phases are available there. This is the SEM images, and we have taken the SEM EDS also there. So this is the composition we are getting, which we have taken in the starting. These are the EM images of all 5 samples. So by seeing the SAD patterns, we can see that there is circular ring patterns are presenting. So we can say that this is a polycrystalline material is present here. And by the HRTM images, we can see there is defect is available inside the material. These are the Raman spectra which we have taken for all 5 samples. So here for Sp2Te3 material A1, G1 and A1 peaks are available Raman modes, and for the tellurium E1 and EG2 Raman modes are available. So this is showing that there is both the phases are available, tellurium and the Sp2Te3 phase. This is the temperature dependent electrical resistivity conductivity. So here it is decreasing with the increasing the temperature, so it is showing the metal-like behavior. And we plot the power law, and by the use of the power law plotting, we calculate the coefficient of A constant value, and this is showing the if the A value is high, and it is showing the metallic behavior is low. So the table is given below. And this is the temperature dependent Seebeck coefficient. So all the samples, the Seebeck coefficient is showing positive. It means all the samples are the P-type materials. And we fitted this Seebeck coefficient with the help of the equation S is equal to XD plus YT cube. By the help of this, we see the carrier impurity and carrier impurity and carrier phonon scattering. This is the thermal conductivity plot with the temperature variation. So here we are getting the different thermal conductivity values for the different samples because of the different specific heat values. Specific heat is directly depend on the this Debye temperature, and that is related to the this that is this is depend on the that is a strain and the atomic size of the element. This is the final ZT of the material which we have calculated by ZT is equal to S square sigma upon kappa. So here for the moderate cooling rate, we are getting the highest directly nearby 0.25. So this is summarize of the top. The moderate cooling rate is the best quenching medium for the conducting material of Sp2T3 material.
Thank you. Sir, now the paper is open for discussion. If there are no questions, so thank you, sir. Now the next speaker is Jyoti Yadav. She will speak on assessment of natural radioactivity in the Himalaya region along the Mandi-Leh highway.
Hello. Good morning, everyone. I'm Jyoti from Physics Department, GJUSA. I'm working under the supervision of Dr. Ranjit and Dr. Pushpinder. My topic of presentation is assessment of natural radioactivity in the upper Himalayas region along the Manali-Leh highway. These are the outline of my presentation. As we all know, monitoring of natural radiation is of great importance to a certain visibility of the for to help keeping the records for future references and for mineral exploration. We all are continuously being exposed to natural uh, out of which 80% are of natural origin and 20% are of artificial origin. Radionuclides are naturally present in our resources, like in rock and soil. The primary source of radiation are the uranium series, thorium series, and the protection radionuclide. In water, the radionuclides which are dissolved or released out of the shores, rocks and sediments contribute to radioactivity in water sources, and the radionuclides which are emanating from the ground surface contribute to radioactivity in the air. The background radiation levels can vary depending upon the geology of the region. We have selected the upper Himalaya region for the measurement of background radiation, particularly along the Manali-Leh highway, as the elevation of the region is so high. The highest elevation is 5 feet to 8 meters. So it is only possibility of collecting samples along the road. We have collected 50 soil, 50 rock, and 30 water samples from the study region. This region is of importance because no previous measurements are done in this region, and the Himalaya region is geologically very active, and this region is origin of rivers and which serves for the drinking and irrigation water for the Indian subcontinent. As you move northward from Manali to Leh, the greenery fits up because the height of peaks goes on increasing and no rain can reach the area. So there will be a high altitude desert. Despite of varied geology, we can classify the soil present there as sandy norms. we have collected water samples from both surface and groundwater sources. Measurement of uranium concentration in the water samples is done using LED colorimetry technique. The concentration measurement of physicochemical parameters in water samples is carried out using Congo, pH, conductivity, and TDS tester. We are also planning to measure the element concentration in the water samples using double layer technique. The soil samples are collected at regular intervals from the region, and the activity concentration of uranium family, thorium family, and potassium radionuclide in the samples is measured using the N-type coaxial HPG detector, which has an energy resolution of 1.8 kV. The gamma radioactivity is also measured using sodium iodide detector, which is still ongoing to have a comparison basically. And the radon and boron exhalation rates in soil samples are also planned to be measured using smart radon detector. These are the spectra we obtained at the Metro software from the soil sample measurements to HPG detector. This is the intrinsic efficiency curve for the HPG detector using the European shore. Concentration of uranium in all the water samples are within the safe limit with an average value of 4.7 micrograms per liter. The annual effective dose, which is 7.93 microsieverts, which is also within the permissible limits of 100 microsieverts. The hazard ratio is also much less than 1. Average value of physicochemical parameters, pH, basic salinity are respectively 6.7, 107 ppm and 0.11 ppt respectively. We observed a slight positive correlation between the concentration of physicochemical parameters and uranium concentration. This box plot is showing the uranium concentration for water from different resources like water for hand pump, river and lake sample. We got only one lake sample from the Deepak channel. It is observed in the preliminary analysis of soil samples that the average concentration of uranium, thorium, and potassium radionuclide in the soil samples is 22, 35, and 369 becquerel per kg respectively, which are less than the world average value of 33, 45, and 40 becquerel per kg. These are the spatial distribution plots for uranium activity, thorium, and potassium activity in the study region. The average value of radiant blend activity is 101, which is also less than the recommended safe limit of 370 becquerels per kg. The box plot is showing the activity concentration for uranium, thorium, and potassium radionuclides in the region, and the spatial distribution plot for radium excellent activities on the right. For concluding, we can say that we have measured the soil rock and water samples in the study region, and this is the first study in that region basically. The uranium concentration in water samples is within the safe limits. Also, in preliminary analysis of soil samples, these are also within the safe limits. And variations observed with activity concentration at different locations may be due to the soil mineralogical content in the study region. And the heavy metal concentrations and radon soil concentration in soil samples are planning to be measured in near future. We are also planning to extend our study region in collaboration with Guardian Institute of Himalayan Technology. These are my lessons. Thank you.
Thank you. Now the paper is open for. Yeah, one person.
Okay, sure. So do you measure the uranium 238 concentration by gamma spectrometry?
Yes.
But in this case, this is always this problem because this is not you measure by the radon progeny peaks.
Yes.
But it means you not measure the uranium 238. You measure the radium.
We measure the decay products of uranium series and then take a weighted average.
Yesterday, even this comment was given to your group. You are measuring radium.
Yes,
Not measuring radium.
Very
Energy.
You have if you have a like the spectra, you can determine the uranium from the protactinium peak, and you can determine if you are able to seal in the the source for 30 days. After that, you are able to determine the reading 56. So this is very good. After that, you will get more results. Sorry.
Instead of mentioning it as uranium, please mention it as radium.
Okay, sir.
Okay. Okay. Thank you, Jyoti. Next speaker is Archana, and she will speak on synthesis of copper nanoparticles for an efficient removal of fluoride from aqueous solutions.
Good morning. Good morning, everyone. I am Archana from Guru Nanak Dev University, Amritsar, presenting my work on the topic entitled Synthesis of Copper Nanoparticles for the Efficient Removal of Fluoride from the Aqueous Solutions. This is the outline of my work. First of all, I'll explain how fluoride can have both bad and good impact on our body. So here we can see that if we consume adequate amount of fluoride, then it can prevent our tooth decay, slows down the loss of minerals from tooth enamel, reverses early signs of tooth decay, prevents the growth of harmful oral bacteria. But on the other side, if we consume the excessive amount of fluoride, then it can lead to dental fluorosis, muscular and skeletal fluorosis, damages the pineal gland, affects the reproductive system and intelligence, that is the low IQ in the children, causes thyroid disorder and neurological damage. This is the pictorial representation how fluoride can have impact on our body. There are some evident reports of fluoride impacts where people have suffered from dental and skeletal fluorosis all over the India. The first one is from the Republic of Kenya. Then the second one is from West Bengal, East Guwahati, Andhra Pradesh, Jammu and Kashmir, Jaipur, Rajasthan. So there can be a lot of reasons where we intake the fluoride, but the primary reason is the groundwater contamination. So in India, here we can see in the map that the most affected states in India are Rajasthan, Punjab, Madhya Pradesh, and Chhattisgarh. In Punjab also, we have seen that the seven southwest region, the southwest districts of the Punjab are contaminated with the high fluoride, and here is one more example where the HSB and his team has presented the high fluoride in the groundwater in Patiala district. These are the permissible limits of fluoride in drinking water by the various agencies. BIS has provided 1 to 1.5 milligram per liter. ICMR has provided 1 to 1.5 milligram per liter, and WHO has provided 0.5 to 1.5 milligram per liter. It is very necessary to remove the fluoride contamination, to remove the fluoride ions from the aqueous solution. So I have chosen the absorption method because it is cost effective, highly efficient, reusable, and high selectivity of absorbents can be used in this method. I have used the copper nanoparticles. Why we use the nanoparticles? Because they have extremely high specific surface area, reduced surface imperfections. They have very unique chemical physical properties. So these all are making them the excellent absorbents, effective towards huge range of pollutants. Not only just fluoride, we can remove various contaminants from the water. The copper nanoparticles are prepared by the co-precipitation method, and then the schematic. This is a schematic of dashboard study where I have seen the effect of pH, absorbent dose, effect of temperature, and effect of time. And the behavior of copper nanoparticles have been studied during the dashboard study. The characteristics of copper nanoparticles are here. The XRD peaks have shown the successful synthesis of copper nanoparticles, copper oxide. This has shown the cubic lattice structure of the copper oxide. The Raman spectra also, the peaks of Raman spectra also shows the successful synthesis of the copper and oxide bond. The SAM image here represents the before absorption image of the copper nanoparticles, and this shows the spherical structure. And after that, after the absorption, when the SAM image was taken, the morphology has been changed. It means there is some absorption on the surface of the copper nanoparticles has been taken place by the chloride. These are the behavior study of copper oxide by the batch mode absorption. We can see that we have got the optimum result on pH 6. The time is 60 minutes and dose limit is 0.5 gram per liter. Temperature is 298. The isothermic model, the Lacnoate plot has shown the maximum fit and it has shown the maximum capacity 69.93%. Kinetic model, the second pseudo second order has fitted the best, and we have got the experimental results 42.8 and it is nearby the 44.7. These are the thermodynamic parameters where the positive value of delta H, that is enthalpy change, confirms the endothermic nature of sorption. The positive value of entropy change indicate the increased randomness at the solid solution interface during the fixation of adsorbate on the active sites of the adsorbent. The negative value of gives the energy shows the thermodynamic visibility and quantity of the sorption process. Here are the conclusions. The excess concentration of fluoride intake is harmful for the human health, and the groundwater in India is contaminated with a large amount of fluoride. Hence, the removal of fluoride from the groundwater is important. So, the copper nanoparticles were successfully synthesized by the co-precipitation method. By using the adsorption technique, it is found that copper nanoparticles are capable to remove fluoride ions with a capacity of 69.9 milligram per gram, shown by the Langmuir isotherm, and optimum pH of 6, temperature 298 K, time of 60 minutes, and absorbent dose of 0.5 gram per liter. The removal of fluoride ions is successfully done. Thank you.
Paper is open for business. Okay, only will take one question.
This is only for environmental aspect you are measuring, not related to radioactive other things. This carbonate, is it carbonate chloride with any radioactive?
Sir, my main work is on uranium estimation in the southwest. Region. But other contaminants are also there, present there. Na? So,
Sorry,
I have tried to remove.
the heavy contamination of fluoride. That's why she is.
Correct. That is why I am asking.
Yeah.
Layer on their wings.
Yellowish layer
Okay.
and the black spots.
Thank you, sir. Now, Ria is here. Ria Upadhyay. No, she is absent. So now we have a tea break of 10 minutes only. So we are running short of time. So,
Before we make, I think we ask Professor Naga, sir. Mike. I request Professor Bajwa sir to present a memorandum to chairperson of the
Within 10 minutes, I think it's better if we come back. We are running shortage of time.
Very wonderful talk, man. I just doing the talk, but it talks
Okay.
working on external electronics.
Electronics, yes.
That's a very fascinating thing.
Yeah, exactly. I didn't go to that. You can observe fermions and all that.
Yeah. ये दो तीन वाले
Hello, 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 hello.
चलो चाय पी के आते हैं चाय पीने आ रहे हैं चलो
Copy करना है
बारह पर्सन से तीन चार लोग
as a part of a traditional culture. Bathing using hot spring water is one of their entertainment. In Japan, using hot spring to treatment. Now, also, Japanese maturated around. And also outside of Japan, especially Europe, it is Hydration hot spring in Japan, distribution map. This is total, this is Osaka. We have many hydration hot springs in the west part of Japan. Agriculture from and also especially balance mind, body, and a good life. Make fun and produce natural healing power inside their body. But so the most so down. Component of the body and their things be more. Sensitivity is solved
one or two questions we can take from the audience.
Stay with me if you wanna. Stay with me if you wanna. Stay with me if you wanna. Stay with me.
emerging scintillators like platinum halides, including bromide and chloride, and different types of PLPs and also PG detectors, and various kinds of pulse processing modules, and compact data acquisition systems supplied by XI company, XC4 also we have, and also manufactured digitizer, and different types of radioactive sources including alpha, beta, gamma, and neutron. So all these kinds of radioactive sources we have in the laboratory. And then neutron sources we have less active californium-252 and high active radium-beryllium source. And we have about 8 faculty members and around 30 research scholars in the field of nuclear and accelerator physics. And I could attend some talks there and also posters where I have seen the work reported on the radiation-induced effects in materials. So, in addition to the gamma chamber available at IUSC, at IIT Roorkee also we have freshly installed cobalt-60 source whose activity is about 500 terabecquerel. So, if anyone is interested, they are most welcome to use this facility as well. And coming to the talk, in the introduction, let me give you some overview regarding the contribution to the environmental radioactivity. One of the biggest contributors to the environmental radioactivity is the accidents that occurs at power generating nuclear sites, that is nuclear plants. We have several examples including Fukushima, where the radiation generated, released in the environment has some kind of a local distribution when compared to the weapon testing. So the biggest contributor to the environmental radioactivity with anthropological source is the weapon testing, where the radiation emitted have some kind of global distribution. So not only anthropologically derived radionuclides, but also naturally occurring radionuclides, they also require regular monitoring, on which this whole conference is going on basically. And it is important to have some kind of a radiation mapping, the purpose of which is to locate and identify the sources of radioactivity within the environment or some kind of different area of interest. And we are also interested in measurement of the intensity of the radiation. So to execute this kind of tasks, we can broadly go either for ground-based surveys or for airborne surveys, right? And in the case of ground-based surveys, one of the biggest advantages is that you can cover, you can have better spatial resolution if you have compromised a little bit with the rate of coverage. And ground-based surveys can be further divided into two types. One is human-based and another is vehicle-based. Nevertheless, the advantages which ground-based surveys enjoys by taking large volume scintillation detectors or large volume acquisition systems is not there with the airborne surveys if we go for uncrewed aerial vehicles. So, in the case of airborne surveys, large crewed aircraft have been used in some of the reports. They have reported some of the documents where aircraft takes large volume detectors and they cover a lot of areas. And in case of uncrewed aerial vehicles, the biggest challenge is that to cover the large solid angle, because more weight of the detectors demands less time for the uncrewed aerial vehicles to acquire the data. So it is important to miniaturize the payload in UAVs. For that, one has to go for the small detector active volume, but that is where we have to compromise with the amount of radioactivity one has to measure for a long time in a localized environment. Okay, and it is important to understand the existing and potentially deployable scintillation detector systems for measuring the radionuclides either from natural or anthropological sources. So if you start from the history of the evolution of inorganic scintillation detectors, starting from Rutherford's famous experiment where zinc sulfide has been used, so we have come a long way until lanthanum bromide was discovered. There was no big leap in the discovery of scintillators after sodium iodide, and a lot of activities are going on in the testing and fabrication of the scintillation materials, and we have around 9.7 million compounds, and about which 1 million are inorganic out of which about 1 million, then 50,000 probably scintillate. The question is how many qualified to be good detectors, right? And the detectors applications mainly depends on what is its energy resolution, what is its time resolution, how fast it can operate, and how transparent it is for the scintillations. And also, is it able, can it separate the different types of nuclear radiation, that is the pulsate discrimination or pulsate discrimination, that means discrimination of different types of nuclear radiation, and whether it is linear to the incident radiation or not. Because at higher energies, there are challenges in maintaining the linearity of the detector. And if the detectors are operated in high radiation environment, how the performance will be there in the presence of different types of nuclear radiation. That is what we need to test using radiation hardness studies. That is where we require either accelerator or we need facilities like gamma chambers. And one of the important property which is of interest in the case of environmental radioactivity measurements is detection efficiency, both total detection efficiency and also full energy deposition that we normally call as photopeak efficiency. And if we take the large volume detectors, it is extremely important to test the performance of the crystal, how homogeneous it is, because the radiation can enter the detector from any direction. So the homogeneity of the crystal has to be tested thoroughly before it is employed in some practical application. And how easy it is to grow the crystals, and under different temperature conditions, how the performance will be there for the crystal. So temperature stability has to be tested. And one of the interesting challenges that researchers are facing nowadays is the crystal itself is radioactive. For example, in the case of lanthanum bromide and lanthanum chloride, if you see, the presence of lanthanum and actinium isotopes which cannot be removed during the crystal growth, they are contributing to the radioactivity up to the energy of 1.5 MeV. So if you are interested to measure the radiation up to the energy 1.5 MeV, the source is outside the detector and the detector itself is also giving the same energy radiation, then it is very difficult to separate the contribution from the crystal from that of the outside in which we are interested. So internal radioactivity is one of the challenges which researchers are facing while doing the crystals. And how good it is in terms of mechanical strength, and is it non-hygroscopic or hygroscopic? Because the moment we use the crystals which are non-hygroscopic, then it has to be encapsulated with some material like aluminum. That will increase the weight, which further increases the weight of the payload if you go for the UAVs kind of vehicles. And of course, most important factor that is the cost involved in the growth of large volume crystals that we are interested in. And regarding applications, immense applications one can see the crystals of scintillation crystals. So we are basically interested in the natural radioactivity and occupy a large part of the research activity under the market share, which has been estimated and reported is about 3,000 crores up to 2020. And the growth of crystals can be done using different methods. It could be either this vertical Bridgman method, or we can go for the Sokalsky technique. The facilities we have in different parts of India, and we should compare the different growth methods. Of course, multi-growth methods dominates over solution growth, vapor growth, and hydrothermal growth. And using this, whatever crystals are grown, they can be used in different ways, like semiconductors. Grow some synthesis crystal, so grow some crystal using vertical Bridgman or solution growth. Paste some kind of electrodes and use it as some kind of semiconductor detectors as well. And scintillators is very well known, and the optical, acousto-optical, lasers and jewelry also, these crystals are widely used. And two main events which are contributing to the growth of the scintillators worldwide, they are CCC, which is headed by CERN, Crystal Clear Collaboration, and also CINT, which is a biannual conference, which has been started from 1992. And it is well known that the choice of the scintillation crystal depends on the requirement of which kind of nuclear radiation we are talking about. If it is charged particles or heavy ions, we know very well that they deposit energy by a Coulombic interaction, and the highly preferred active volume media, they are either gas or solid. And if it is gamma rays which have no mass and no charge, we go for either scintillator or semiconductor mainly. And if it is neutron which have mass but which have no charge, then either we go for liquid medium or solid medium. And so the motivation mainly that we are focusing in this part is how efficiently it can resolve nuclear radiations with better resolution, and how efficiently it can detect different types of nuclear radiation, and if possible, one can explore, is it possible to discriminate the different types of nuclear radiation when we go for the environmental radioactivity? And the time-tested scintillators like sodium iodide and cesium iodide, they have been quite widely used by various groups for the environmental radioactivity. And recently, you can see several papers that are talking about the lanthanum bromide as well. And most appropriate detection materials and the layout for radiation mapping is also important, which can come out from the realistic Monte Carlo simulations. And one has to zero upon on the energy resolution and the detection efficiency, which are important when we consider the small volume radiation detection system for the environmental radioactivity. And when we come to the energy resolution, it is important to ensure that the light yield emitted by the scintillation crystal, it has to be better, like it has to be like 50,000 to say 1 lakh if possible. And the highest light yield which has been reported for scintillation crystals is strontium iodide, which is facing problem in having large volume. And in terms of lanthanum bromide and cerium bromide, they are more or less equal in terms of resolution. Coming to detection efficiency, it is important for the crystal to possess better atomic number and better density. And recently reported crystals that are gadolinium, gallium, aluminum, garnet. GAG crystals, they have been tested for not only the detection of thermal neutrons, but they have been proved to be highly useful for the detection of high energy gamma rays. And of course, lanthanum bromide is always there. And barium germanate, because of its high density, one can use the detection. One can use it for the detection of gamma rays, but its major problem is very poor energy resolution. So one has to choose the scintillation crystal as per the requirement. Do you prefer high efficiency for better intensity measurement, or you want to separate the energies of the radiations? And another challenging part is that when we use the scintillation crystal, what kind of photo sensor we use? Because the moment energy deposit is converted into light in visible range, then the photosensor choice also comes into picture. Either you go for the PMT, which occupies large space, and a silicon photomultiplier, which occupies less space. But the problem with the silicon photomultiplier, as we know, is it is highly temperature dependent. So spectral matching is a key requirement, and the inclusion of small concentration of dopants to achieve the spectral matching is a very well-known technique. And so before employing the large volume detectors for the environmental radioactivity using UAVs, so it is important to perform the realistic Monte Carlo simulations. In this particular report, they have tested the performance of the crystal by increasing the length of the crystal from 25, 50, and to 100 centimeters, and the source detector separation has been maintained constant. And here you can see the spectra for 3 different lengths of the crystal. Width and breadth is same, and source detector separation is same. And as shown in the spectra, it is very clear that as the length of the crystal increases, then the distance traveled by the gamma rays coming from thorium, uranium, and the cesium. These 3 are important radioactive sources that present mainly when we have some kind of weapon testing or some kind of nuclear power accidents. Otherwise, also nature always emits this thorium and uranium, which many people have talked in the conference. So the realistic Monte Carlo simulation gives us an idea for a specific crystal whether we are able to separate the peaks or not, and what is the impact of the crystal thickness. This can be done by GR4, which is an open source toolkit provided by the CERN. And if we carry the same simulation for the cesium, which emits widely use the 662 keV gamma rays, there is a 20% increment in the efficiency when air is ignored in the simulations. But practically, when a source is placed away from the detector, air is always present. So we need to consider the effect of air also in attenuating the gamma rays. So while using the detectors in applications, mainly for the intensity measurement, one has to consider the presence of air in the simulations. And these are some of the key properties of the scintillation materials, starting from the time-tested sodium iodide to strontium iodide. And you can see the light yield varies from say 8,000 for the barium germanate, which gives very poor resolution, to 1.15 lakhs for the strontium iodide. And energy resolution changes from say 2.8 to the largest resolution one can imagine for the barium germanate because of its high density but very poor light yield is 16%. So the choice of detector will be controlled by all these parameters. And the simulations can also be performed for understanding the light versus the wavelength. And you can see the cesium iodide and gas simulator, they have almost same spectral matching, ranging from 450 to 700 nanometers. And if you see the thorium 232 spectrum and uranium 238 spectrum are 4 different simulators. Here we have taken cesium iodide, lanthanum bromide, and LOSO crystals. And the ability to resolve the peaks of different energies can be clearly seen when we measure the spectrum of thorium and uranium, when we try to use these crystals in environmental radioactivity. And clearly one can see that lanthanum bromide is far away when we compared to other crystals in terms of resolution and also due to high density. In case of a problem in growing large volume crystals, an alternate way is to use the small volume crystals. Then you test the performance of single crystal and then you take 3 single crystals and then you add the signals and you get the total energy deposited in the crystals. Then one can see that there is a huge increment in the efficiency as expected when we combine the single detector with the triple detector. So how to arrange the different large number of small crystals if you have less money, or if the manufacturer says there is a problem in growing the large volume crystal, then you can go for this kind of combination. And of course, when we compare the single volume compressing the 3 individual volumes, there is a small change, but we can always go for this, provided we have the pulse processing electronic modules. And our group is actively involved in testing and characterization of different types of detectors, starting from 1 inch by 1 inch lanthanum bromide. The work has been carried out at TAFR. There, we have reported a unique technique to find out the efficiency by considering the double gamma emitter like cobalt-60. Because if you consider cobalt-60, 2 gammas are emitting simultaneously, and when they enter the crystal simultaneously, they will deposit the sum energy. And you are using the individual counts for the corresponding separate energies. So one has to correct for the effect of true coincidence summing using some physical constraints, and then one can find out the efficiency for the individual energies that we have reported. So how these efficiency measurements are important in terms of environmental radioactivity, one can see from these results. And this method has been tested not only for single detector, but also for large volume detectors. Here, 32 detectors of sodium iodide, which has been mainly fabricated for the studying infrastructure nuclear reactions. So there we have 20 hexagons and 12 pentagons. And this method of finding out efficiencies for 2 different energies using single source, that is cobalt-60 that we normally use for calibration detectors in our teaching laboratories. This unique method of mathematical formalism is helpful for finding out the efficiency. And one can carry out the GL4 simulations and find out after the correction how the agreement is there for efficiency. And the search for new scintillators, it is a continuous process because the germanium scintillators, nobody can beat it in terms of energy resolution. But the problem is we have to cool it either electrically or using liquid nitrogen. But the problem with the hybrid germanium detectors is its cost and also its efficiency is quite less when compared to the scintillation crystal. And the problem with the scintillation crystals is that its efficiency is very good, but resolution it can never match with the semiconductor detectors like germanium. But one has to use the trade-off understanding in order to use it for different applications. And in terms of lanthanum bromide, when we see it has light in about 60,000 photons per eV, and its decay is also really good. In terms of picoseconds, one can expect 300 picoseconds. And compared to sodium iodide, which gives you 6 to 7% resolution, lanthanum bromide gives you 4% resolution. And one of the important advantages is that it is highly stable against the temperature variation. This is one of the important utility in environmental radioactivity. And its high density ensures the excellent efficiency. Yeah. So there is a need for large volume crystals, and there is a challenge to grow bigger crystals. So once we have the problem with bigger crystals, the only way is that you combine small crystals. And in this case, we have combined 4 rectangular lanthanum bromide crystals, and we have tested the performance against the single volume in scintillation, in GL4 simulations. And large amount of work has been done with lanthanum bromide detectors, and it has been proved that it is next to GAG, which we have reported recently in terms of efficiency and also resolution when compared to sodium iodide. And if you compare the efficiency of lanthanum bromide and the barium fluoride, of course they're more or less equal. But the problem with the barium fluoride is that as we know very well, its light yield is poor, resulting in very poor resolution. So for high image detection, either you go for large volume single crystal lanthanum bromide or you take the combination of lanthanum bromide. And for single large volume crystal, it is important to test the performance. Thoroughly calculation has been done in terms of the resolving various peaks for different gamma sources. Its linearity has been tested, and this is the internal radioactivity. You can see how radioactivity without any source and it highly shielded with the hundreds of lead bricks. We have the diagram spectrum of the crystal, both lanthanum bromide and sodium. You can see clearly various peaks which are given by the crystal itself. So as I said initially, the removal of the peaks corresponding to the radiation emitted by the crystal is a challenging task. Of course, if you are interested in measuring the energy beyond 1.4 milli, lanthanum bromide can be confidently used. And this is the results from the homogeneity. At every point of the crystal, when we ignore the front surface, the performance has to be linear because radiation can come into the crystal from any direction. And under this kind of highly shielding, the performance has been tested. And the high energy up to 22.5 milli has been seen with the large volume crystal. And similarly, we have taken for the square bar arrays of lanthanum bromide. So lanthanum chloride, which is a part of lanthanum halide crystals, has also been tested for this measurements of intrinsic resolution using Compton coherence technique. And one of the participants in this conference, Sanjit Kaithura, who is now working in the field of environmental radioactivity, he has recently published a paper on lanthanum chloride. And one of the important techniques to understand the origin of energy resolution. After the efficiency measurements, just I'm quickly going through the interesting technique where HPGE can be used as a reference detector and the scintillation detector can be used as a test detector. And understanding the Compton coincidence between these two detectors, one can get the excellent resolution information of the scintillation crystals. And this we have done with the BC501A liquid scintillator, which is very poor detector for the gamma rays, but we are able to get very good peak for the BC501A using this Compton coincidence technique, which is otherwise impossible. And resolution also has been plotted, which is not possible in general. And using Compton coincidence technique, one can get the resolution studies. And finally, let me show you some of the important results for the GAC scintillator, where alpha and gamma has been separated very clearly. And one of the important advantages of this GAC scintillators is highly unhygroscopic. So there is no need to encapsulate this crystal. But there is a challenge to grow it in bigger size. And efficiency measurement also have been done. And it is clearly established that presently no scintillator can beat the GAC scintillator in terms of both efficiency and the resolution. So you can see the relative total detection efficiency and the photo peak efficiency. And the total simulations and also measurements have been done and they have been reported. Yeah. And GL4 simulation shown here. I will take 1 minute. So the results have clearly shown that GAG has shown highest efficiency when compared to all other scintillators. And also resolution wise, it is comparable when we take the sodium iodide. And to summarize, the evolution of scintillation crystals, it stems from the multidisciplinary approaches, which is tuned to the needs of the specific field of applications. And the needs of the end users are permanently changing. A lot of inputs have, it is yet to come from the community of environmental radioactivity. And the choice of photo detector, signal processing, and the computing and data flow capacity. It also requires thorough theoretical understanding of the scintillation mechanism and also experimental investigations. They are also equally important. And many thanks to the students and my collaborators on TIFR and BRC, including Mr. Gadkari and Dr. Mohit Tyagi, and my PhD students and my ex-PhD students and postdocs. I sincerely thank all of them and this opportunity. Thank you so much for your attention.
Thank you, sir.
Sorry for crossing scheduled time.
For discussing your centimeter metal for natural radioactivity detections. Now paper is open for discussion. Yeah, Baju sir.
Sorry, Councillor, really quite informative and quite strength talk here.
Thank you.
But basically, what I was interested is you have been working on wide range of detectors, no doubt. And of course, especially if I just compare sodium iodide with lanthanum bromide, it has a more efficiency, more resolution, and its photoluminescence is 63,000 as compared to
Yeah, so
45. It's very less. But there is a one major issue of its own radioactivity. How we can remove this particular problem?
So as I said, twice it is difficult to separate from the outside radiation. The energy is up to 1.4 MeV. Up to 1.4 MeV. If outside the outside radiation is giving same kind of energy, then it is challenging to reduce. Count the contribution from outside. But if it's beyond 1.4 MeV, lantern movement is ideal candidate. But there are methods to remove it. For example, if you take inside the laboratory, you take for several days this contribution from the internal radioactivity, and then you take the data from outside. Then using some kind of normalization techniques, one can reduce the contribution from the crystal itself. But yes, more measurements are required from the lantern movement. But as of now, it is.
As the comparison is concerned, still today we can go mainly for sodium iodide.
Yes. But I have seen at least 5 or 6 papers in the measured radioactivity where people have using lantern movement. So because of time constraint, I cannot show the data.
And secondly, whether your laboratory can be used by anyone free of
Most
cost or
welcome.
some.
Most welcome. That's one of the reasons I am here.
Yeah, but some paper has to be made for analysis or it's free of cost?
It's free of cost. Very most welcome. We want facilities to be utilized for all communities.
Thank you, sir. One more question. Now, thank you, sir, for delivering wonderful talk, very informative.
Thank you.
Now, we have next paper for discussion. Radionuclide contains soil samples from the eastern trace of radioactive fallout from the semi-Arctic test site, and this will be delivered by Professor Hibur.
This is beginning with my name, Kovac. This is this one, which is the okay. So thank you very much again for the possibility to give a presentation, but this is instead of my student. She was not very brave to give the presentation, so I would like to present her presentation. Now the separate extra site. Maybe you know, in this technical instance, this is now in Kazakhstan now, there is almost 600 atomic bomb tests after 100, after the second war. It was used by the Soviet Union, the test site. The test site is relatively big, it seems it's almost 10,000 square kilometers. This is really huge, and there are many villages here and many inhabitants living here. And we would like to we would like to estimate the risk of the radiation here. So, okay, this is some place, some picture about the central infrastructure. As you know, there was some main part that was really contaminated. And the first one was from 1949 and almost about 90. It was finished after the collapse of the Soviet Union. And there was a lot of atomic bomb tests even on the surface. So, but all the atomic bomb tests was caused a relatively huge not air pollution, deposition. And due to the cloud, due to the dust. The biggest one was 1949, and now we would like to check that this territory is possible, is acceptable, cost contaminated, or is it possible to close or evacuate persons who live here. So what you will see, mainly the main problem in this area not only the gamma module surplus, because the gamma module surplus is not really important. Only the main problem is the suspension on the dust. So you can see that it will be tested here, and because of the situation of this huge bomb test, the main radioactivities remain here from this bomb test. So there are some weapon these devices not used for the Germans really ICT terrorize sending a weapon microscope of course gamma spectrometer systems and this
So in this picture, the natural artificial it's a function of distance. See, it's not working. Yes, maybe. Oh, sorry. Maybe I turned it off. Okay, maybe.
From the phone.
Is it okay?
No.
Okay. Is it okay? Okay, so okay. So maybe you can see here the natural radio distribution is really normal. You can see that the potassium given the lead 210 is almost just like the normal soil on the natural background. In this area, we take almost 100 samples the one case, this is altogether 500 samples, and we measure different parameters in soil. So you can see the artificial medium concentration, even the uranium. Sorry? Okay. And really rich. So back to the, so you can see the uranium is on the 80 concentration is not really high, but it is sorry, this is the natural. Yes. So, so this is always in the normal concentration. On the next slide, you can see some non-reactive concentration only due to the main compounds, main source, the main isotopes contained by the aerosols. So you can see this is really normal concentration. So we can see some interesting situation. For example, we don't know what is the real reason, but after almost 20 tests around the awareness concentration is much higher than the other things. So maybe we should find the reason. So you can see here is so, and you can see that I don't know why it's so one slide is missing. If you have jump. So yes, I don't know why this is. Okay, maybe I will jump on this. Okay, so you can see the artificial regulatory concentration. And you can see the evolution is not very high. It's been several kilogram. And in case of the plutonium concentration is still high, more than 120. Of course, sorry.
So you can see there are some relevant concentrations, some isolation, some concentration in the soil. And finally, the conclusion, according to our idea, the concentration, relative concentration in the soil is not too high. So even this area is possible to be the farmers, the inhabitants, because there are a lot of farmers here. It is the risk of leading to the radiation is not really higher than acceptable. Of course, this is contaminated, but not highly contaminated enough to the extent. So thank you very much.
Thank you.
Now paper is open for discussion. Any question? So, thank you, sir.
So thank you very much.
For giving this lecture. Now, next oral presentation we have study of soil radon anomalies and non-spheric situation preceding Nepal earthquake of 2015 by Sally Chaudhary.
Good afternoon. This is Sally Chaudhary. I'm going to talk about our work on the multi-parametric approach for studying earthquake precursors. And as a case study, I took the Nepal earthquakes of 2015, and I studied soil radon anomalies and atmospheric situations together that preceded those earthquakes. Now, this work, the idea for this work originated in 2021 during the lockdown when nobody could go anywhere. So I used data that was already there in order to do this study. So in case of earthquakes, I mean, since it's a very dreaded phenomenon because it cannot be predicted and it's a fatal thing. So the idea is that apart from like disaster management and risk mitigation, which engineering safe and stable structure so that they do not fall during earthquakes or do not cause much hazard, there is also this idea of seismic precursors or the seismic precursors, whatever. So the main idea is that to make predictions of earthquakes like weather predictions. Of course, we cannot do that because there is a very complex phenomenon, but people are trying all over the world in order to do this. So short-term precursors are actually those that would be that actually appear within 2 to 3 weeks before the earthquakes. And among them, we focus on gas emissions because inside the earth crust during the earthquake preparation phase, especially towards the end, when there is a lot of fast stress and strain changes within the crust, the fluid flows are extensively affected by the faulting process and they can be easily detected. And among them, I chose radon gas because it is present everywhere. Since all types of rocks in the earth crust contain some quantity of uranium, and radon is the product of that chain. So it's present everywhere, being radioactive, it can be detected easily. And of course, a fraction of the radon that is generated inside the crust can migrate by different processes until the earth crust and then get exhaled into the atmosphere. Of course, I did not focus on the exhalation. But anyway, so the main thing is that at every place on the earth, there is a normal radon emission particular to that place, depending on local geology and all, and also of course on meteorological parameters. However, before earthquakes, it has been observed that there are anomalous variations in that radon concentration or radon emission pattern in that place, and they are related to the earthquake-related stress strain changes, and these anomalies can give be considered as precursory signals. Now, in this case, I considered as anomalies only those spikes in the radon time series, which were more than twice the standard deviation from the average using the definition given by King in 1980. Of course, like I said, meteorological parameters also affect it, rainfall especially affects it, and then there are local geophysical and geological features. So the thing that I did is I punched two different precursors together, studied them at the same time. I mean, they were recorded at the same time and studied simultaneously in the same place. So the monitoring station is the same, and then I analyzed them also together. So the atmospheric precursors, that is the scintillations in the ionosphere, they are also generated because of radon gas coming out of the soil. So during during the earthquake preparation phase, when there is anomalous changes of radon, more radon is coming out from the crust, then that radon can, like Dr. Roy was saying, he had observed radon gas in the atmosphere before earthquakes, which means that more radon gas coming out from the soil, of course, gets into the atmosphere, and radon being an ionizing gas, it emits alpha particles causes ionization of the air, and then there is secondary ionization, and all these forms are sort of at every level of the atmosphere, there is a different concentration of ions, and they form an electric field that penetrates until the upper levels of atmosphere, including in the ionosphere. And in the ionosphere, these things are registered by the positioning satellites as scintillations. Now, such sort of scintillations can also occur due to geomagnetic storms or solar flares. However, this is already said it anyway. So the year 2015 was in the declining phase of the solar cycle, so solar flares could be ruled out. And also there was the time period that I studied during April-May 2015, there was also no solar, geomagnetic storms, so that could be ruled out also. So I studied soil radon activity was measured in my campus at two locations, separated by only 200 meters. The original idea was different. I used the data that was already present, and the ionospheric situation data was taken from another university in the same city. It's very close, and I studied them together. So this is the setup for the radon monitoring in soil. It was done by the solid-state nucleotide detector CR39, like it was discussed extensively on the first day. So in this case, I had a plastic cup of like 3 centimeters depth, and at the bottom of the cup, I attached 1 centimeter cross 1 centimeter CR39 plate, and the top, like the open end of the cup, was covered with a membrane, latex membrane of 20 micrometer thickness in order to cut off the thoron. And then this entire cup and the thing was put deep inside in the shaft within the ground at a distance of only 1 centimeter from the soil. So, and the depth of this shaft, there is a mistake here. The depth of this shaft was almost 1 meter. The exposure time was 24 hours, and then I etched it in like it was etched. So it was etched in these conditions with a sodium hydroxide bath, and the observation was done with microscope. Now the parameter I focused on was tracks per centimeter square, because the number of tracks that could be observed under microscope. And the principle was that the track density is proportional to radon concentration in the sample. This was how the satellite scintillation was detected using the GPS. So this is the polar plot for the satellite recording the scintillation. So only on 3 days before the earthquakes, scintillations could be seen. The first day on which it could be seen was April 23rd, and there were like the black ones show the satellites that did not show scintillations, while the colored ones the parts of the satellites showing scintillations. They were generally seen in the 15 hours. And the next day was on April 29th, And the next day that the simulation could be seen was on May 11th, and most of these segments were showing circulation, almost all of them went to the north of Kolkata, the monitoring station. And this is the how the soil radon anomalies, the soil radon data with the meteorological parameters in the same location. And these were like the anomalous fluctuations. Of course, there were two before they were not followed by any regional aspects. This was the thing that was seen from another station, the other one in the campus. So this is the data for the earthquakes and the radon anomalies. It is seen that on 20th of April, the first anomaly was seen, and the earthquake that occurred, the first Nepal earthquake occurred on 25th, 5 days later. And the second one, the anomaly was on 29th, and it was the earthquake that occurred was on 12th of May. And like it was like a because the time was like within 2 weeks in both cases. Like I said, two more anomalous fluctuations in soil level time series was also seen, but those fluctuations were not followed by earthquakes, and there are also no ionospheric scintillations. So the main takeaway from this work is that using two different precursors, I could just rule out some spurious pulses in the radon time series that were not followed by earthquakes. And also the idea is that using different parameters, using different precursors from the same station, it is much easier to identify properly the genuine anomalies. So these are some references I used. And I am thankful to everyone, and especially RADNET-IV organizers for giving me this opportunity, and everyone else who supported this work. Thank you very much.
Thank you, ma'am. Now paper is open for discussion. Yeah.
Sorry.
Satellites have detected some scintillations, right?
Yes, sir.
So these scintillations are mainly originating from?
The scintillations in this case, the scintillation can originate from many things. But in the ionosphere, they are originating from interactions of ions, of course. So in this case, those interactions happen, like those reactions were happening in the ionosphere because there is this radon is coming out, it is ionizing like every level of the atmosphere gets ionized, not just because of the radon, but also the gases that are ionized, they will ionize secondary molecules, and this go on until the magnetosphere.
And what is the wavelength range of these scintillations? Any idea?
Well, the satellites were detecting it in the L1 frequency.
Your conclusions are missing. You have not presented any conclusion.
Well, I was like saying the conclusions at the same time.
Okay. But you think that I think you have shown some can technique you are buried inside.
Yes.
So you are often change those SSND films to measure. So you are often changes those SSND films. For how much time you are taking those SSND? 24
hours. They were exposed for 24 hours. Yes, every day there is one. Like we change it every day.
I think the digital radiometers are much better than these SSND because there is interference of many decay products are there, leakage is there.
Of course, there is. So the idea was not to measure the exact radon concentration, but to see fluctuations, changes. So we are not focused on the exact radon concentration first. And secondly, it's that LR and CR are the things that we have. We don't have crystals, so we used what we had. But thank you for the thing because yes, crystals are a lot better.
Okay, thank you, ma'am.
Studies, we do not care about radon or whatever.
Thank you, ma'am. Next presentation is characterization and performance of coaxial HPG detectors by Sanjeev Singh Kankara.
Good afternoon to all of you. Myself Sanjit Singh Kendra, and I'm going to present work based on the characterization and performance of the coaxial HV detector, that is high purity germanium detector. This is the layout of my presentation. So as we know that the gamma ray can interact by three ways, using photoelectric effect, component scattering, and pair production. And these gamma ray can be detected using the various detectors, such as the gas detector, that is based on the principle of the ionization, scintillation detector, the production of the photoelectron from the scintillating light, and semiconductor detector, those produce of the electron hole pairs. So gamma spectroscopy is the non-destructive technique, and high-purity germanium detector contribute a significant contribution due to its high energy resolution. Hence, to increase the measurement accuracy in the gamma spectroscopy, the selection of the best high-purity germanium detector is essential for a particular type of the measurement. Using this motivation, we have performed the characterization and performance check of the two different type of HV coaxial detectors, which has been checked based on the various parameters such as the energy resolution, efficiency, minimum detection efficiency, activity, and peak state. Further, we have also checked the scanning using the distance scan, lateral scan, and radial scan while using various gamma ray sources. At last, we have performed the intercomparison between the performance between the P-type and N-type detectors, and with the diagram study. So this is the detectors and electronic specification. Both detectors are comparable to volume. However, N-type detector is quite large as compared to P-type detector. With the P-type detector having the aluminum window, while N-type detector has the platinum window, which is thinner than the P-type. This is our experimental setup. Here, HV detector is surrounded by the light shading, and the signal are produced through the electronics and finally acquired in the mesh code data acquisition system. The whole data is analyzed using the LAMP software that is provided by the TI4 Mumbai, Linux Advanced and Multiple Parameter System. These are the performing parameters that we have estimated or evaluated in the present work. So prior to actual measurement, the optimization and system calibration is important. Hence, we perform the major optimization as well as the calibration. From this graph, we can see that there is a perfect correlation between the channel versus energy, and in this plot, we can see that there is a strong correlation between the absorption full width at half maxima with the energy, which shows that the calibration was in good condition. Next, this is a spectra acquired using the 57 forward at low energy, and this is a spectrum acquired at the high energy. So after calibration, we have performed we have also checked the major checks using the FWHM, FWPM, full width at half maxima, full width at the 10th maxima. And this data was compared with the literature with the nominal value as well as measured by the manufacturer. Efficiency using the point sources was also estimated, evaluated, and there was a slightly difference at the low energy. Hence, in N-type detector, it was found that the high accent at below the 150 kV, while the trend was going same for the low detector at the above the 150 kV. So this is a minimum detection activity was also estimated for to find out the detection limit at a low as well as a high energy with the various sources as well as with the different distances. So it was found that the MDA for the both detectors above the 150 kV was same, but however at low and almost comparable, but at low energy n-type detector was quite high efficient. And above the 150 kV, the detection limit was found varying within unity. Further, the scanning of the detector was also performed. So, distance scanning was performed along the cylindrical axis of the detector, while the radial scanning was along the diameter of the detector, and lateral scanning was performed parallel to the cylindrical length of the detector. From the distance scan, it was found that there was a difference between the p-type and n-type detector at low energy, which is around 26%. But at high energy, it was nearly same. As well, from 20 to 30 centimeter, the absolute efficiency was nearly equal. From the radial scan, again, radial and lateral scan, there was a difference was found at the 88 kV, which is a low energy. The difference in the radial scan was around 45%, while in lateral scan it was around 39%. At high energy for radial scanning, it was nearly around the same, but there is at 1115 it was a difference because of the crystal detector that was facing the old gamma length from front side. In lateral scan, the detector was high efficiency was found at the larger length for the entire detector. That may be due to the larger crystal length of the entire detector. Further, ambient background was also measured in both detectors, and it was found that there were in above the 150 kV, the spectrum was nearly equal to same, but below the 150 kV, the spectrum there was a difference, as well as there was some low energy gamma line was also observed in the p-type detector. We saw that below the 150 kV, the entire detector performed better than the p-type detector. This spectrum was further analyzed for the integral window, and it was found that there was a relative difference in this energy window, which was found around 50%. While measuring the environmental radioactivity, the main energy range, integral window from 40 to 2700, it was found around the second highest, around the 23%. Now, using the entire detector, the shielding was using the shielded material. The low background was also applied, and it was found that there was a reduction. There was a reduction around 91% in low energy range, while in the main energy range, laser environmental radioactivity, there was a reduction around 86%. So, and from the spectrum, we can see that most of the gamma lines are of the low background in the shielded configuration. And also the order of further the laboratory background was also measured, and the order of the natural radioactivity was found. Highest contribution was found the 40K, then 232 thorium, and last 2 to 6 radium. Finally, on the summary and conclusion, we have studied in this work that the characteristics of the NP-type detector were studied in the wide energy range from 80 to 1408 kV. The orientation, further we study the orientation of the crystal as well as the SF efficiency at various points. We have studied the detailed characterization using the closed scanning, and intercomparison between the N-type and P-type detector were also performed for the efficiency as well as background analysis. In N-type detector, it was found that it is more suitable for below the 150 kV, and contribution, the highest contribution was found from the 40K. Hence, the characterization and performance of the load detector was found at a good in working condition. In future scopes, we will incorporate the more complex theory, improve the sensitivity of the setup, and further we will measure and analyze the environmental radioactivity using the soil sample, and we will analyze the radiological impact on the public health. Thanks. I would like to acknowledge here the Agriculture, Water and Water Technology Hub that was established by the Ministry of the Science and Technology, Government of India at IIT Roper in the framework of the next mission of the interdisciplinary physical system. I would also like to thank the government for the Dr. fellowship. Thank you for your time.
Now paper is open for discussion. Any question? No question. Thank you, Sanjeev. Next presentation is systematic study on influencing factors of millennium and other elements in Ganga River by R.S. Aswal.
Okay, so very good afternoon to all of you. I am Dr. Ravinder Aswal, and I am from the Delhi University Static TV. And today's my topic is systematic study on influencing factors of the uranium and other trace elements in the water. On behalf of our team, I would like to present the paper before you. Next. Here is some background about the study. Occurrence of uranium, prevalence of uranium in Earth's crust is mainly in uranite, monazite, and zircon minerals. Monazite mineral is also consists of thorium besides of uranium. Uranium can also be found in trace amount in all three types of rocks: igneous, metamorphic, and sedimentary. Soils, groundwater, and surface water. It enters to the ground, environment as a result of leaching from natural deposits under geogenic activity, and under the anthropogenic activity, it also releases from the nuclear industries, nuclear power plants, and the combustion of fuels, including phosphate-containing fertilizers. Occurrence of other trace elements, in addition to the geogenic activities, industrialization, unplanned urbanization, and inorganic agricultural practices at unprecedented level has given birth to the water pollution due to elevated trace elements concentrations. Various elements in minute level are essential for the human body to proper function. Some trace elements are not desirable but non-toxic, whereas others remain as toxic due to their chemical nature. Identification of the contamination due to trace elements in Ganga water using reliable technique is yet required to be scientifically evaluated. Therefore, the motivation of the study is due to Haridwar district is mainly depends on groundwater, forest drinking, and other domestic needs. Increased population of the Haridwar coupled with millions of floating pilgrims and tourists has overburdened the available groundwater sources to meet out its requirements. Likewise, Kolkata, where most of the public drinking water supply is made available through the Ganga water, after proper treatment, same objective can also be adopted to properly implement in Haridwar in order to reduce the pressure on lowering of the groundwater table, as the lowering of groundwater table will accelerate the elevated concentration of trace elements in its sources. Therefore, present study was designed and carried out to find out an alternate source of the potable water in plain area of the Haridwar. Here are the objectives of the study: assessment of water, Ganga water at 6 different locations
from origin point of the Ganga Canal, including exit point of the Ganga Canal in Uttarakhand with a reference site for uranium and 7 other trace elements concentration as per the WHO guideline values. The Bureau of Indian Standard is the national drinking water regulatory agency, which may either be inconsistent with the WHO guideline or may give some relaxation as per the economic condition, available treatment technologies, and the available water resources in the country. Therefore, the entire study was conducted for a period of 1 year, June 2020 to May 2023. The entire 1 year period was further classified into 4 seasons. Summer season, autumn season, winter season, spring season. Spring season is yet not covered in the study due to this season was started just 3 days ago, and after the conference we will cover this season also. Use a multivariate analysis to assess the possible cause and sources of pollution in Ganga water. Here is the novelty of the work. First study of its kind in the Haridwar district. For the study of uranium besides other trace elements in the Ganga water, application of multivariate analysis to find out the possible causes and sources of the contamination in Ganga water using principal component analysis, two-tailed correlation, and cluster analysis. Here is the study area map. The Ganga river is further bifurcated into three different parts. One is the main branch, which will move ahead towards its destiny, while one branch will move towards the west direction. It is called Western Ganga Canal, and one branch is moved towards east direction. It is called Eastern Ganga Canal. So Western Ganga Canal was taken for the study purpose. Here is the collected water samples were further analyzed using ICBMS instrumental technique, and the obtained data set was further processed under SPSS software for the extraction of principal components, cluster analysis, and correlation metrics. PCA is an effective tool used for identification of chemical constituents present in water which share same origin and their relationship with each other due to minimizing number of dimensions present in raw data. The chemical components with similar behavior generally share similar principal components. It is used to extract significant pieces to reduce the inclusion of less significant data. Loadings have further been classified into 3 categories: strong, moderate, and weak, corresponding to their values above 0.5, between 0.5 to 0.75, and 0.5 or 0.3 to 0.5. Cluster analysis is further performed based on the Watts method with squared Euclidean distance mode, and two-tailed correlation analysis are used for the source determination. It is performed to construct a cluster among sampling sites based on their pollution load in the study region. Here are the results. Except lead at one site, all the values were obtained within safe limit of the WHO as well as Bureau of Indian Standards. Here is then this entire data set was processed under SPSS software for the extraction of PCA. A total of 89.314% of the cumulative variance was extracted for 3 PCs, that is PC1, PC2, and PC3. PC1 has strong factor loading over 3 trace elements, that is chromium, cadmium, and mercury. PC2 has also strong significant factor loadings on the nickel, molybdenum, and lead. But in case of molybdenum, it was a negative factor loading. It means the source of origin will be different than that of other 2. And the PC3 has only 1 factor loading on arsenic. Here are the some possible sources of the geogenic activity as well as anthropogenic activity, which may be responsible for the significant factor loadings on different elements. Here is the cluster diagram. This sampling site number 2, due to this pollution load. Due to the dissimilarity in the pollution load, it was clustered into different groups, while remaining 5 were clustered under different clusters. There are some remediation techniques of uranium other trace element from the water. The bioabsorption and bioremediation is the promising technique for the due to low cost and chemical free operations without any disadvantage for uranium removal from the water. As far as other techniques are considered, the biological treatment also do not have any disadvantage, but it is yet to be implemented at a larger scale. Here are the conclusions. Uranium concentration in allied groundwater was found well below the WHO prescribed limit. Ganga water was found suitable for drinking purpose, except lead at one site during the summer season. And the study is useful for the effective management of Ganga water in the studied region for further use. Thank you.
Thank you, sir. Now, paper is open for discussion. No question. Thank you, sir. Next oral presentation is gamma ray spectroscopic analysis of radium, thorium, and potassium in soil samples of Kumar Himalaya by Poonam Singh.
Good afternoon, everyone. I'm Dr. Poonam Singh. Topic of my presentation is gamma ray spectroscopic analysis of radium, thorium, and potassium in soil sample of Kumaon, Himalaya, India. These are the outlines of my presentation. Now the background of my topic. As it is a well-known definition of radioactivity, the continuous emission or transition of energy in the form of waves or particles through space or material media. The radioactives are mainly two types: man-made radioactivity, natural radioactivity. As we are talking about the man-made radioactivity, it is from the various nuclear energy program, and the second one is natural radioactivity, and we are focusing on natural radioactivity, which is from various radionuclide observed in nature and formed in natural process. As we are talking about the radiation doses, the radiation doses is also depending on the two parts, which is from the natural sources and artificial radiation sources. If we are talking about the radiation doses due to the natural sources, this is 2.4 millisievert per year, and due to the artificial radiation sources, 0.61 millisievert per year. And the natural sources are broadly classified into three groups: external sources of extraterrestrial origin, sources of terrestrial origin, and the third one is internal sources. The first one is external sources of extraterrestrial origin, which is called cosmic rays. It is contributing 0.39 millisievert per year. And the source of terrestrial origin, the radioactivity presence in Earth crust, in atmosphere and building material. It comes in source of terrestrial origin, and the contribution of 0.48 millisievert per year. And the third one is internal sources. Naturally occur nuclei taken into the human body through the injection and inhalation. So the radon and boron, their decay products contribute 50% of natural background doses. Now we can see this in this picturization. This is the distribution of radiation doses. We can see here 50, more than 50% radon is contributing in the radiation dose. The next one is radionuclides. Natural radionuclides are of two types: cosmogenic and primordial. The cosmogenic radionuclides produced when high energy cosmic ray particle undergoes nuclear reaction with the nuclei of atom present in the atmosphere like oxygen, nitrogen, and argon, etc. And if we are talking about the primordial radionuclides, isotope of heavy elements in existence since the origin of the Earth together with the daughter products. We can see here the main primordial nuclide, potassium, Rb, and thorium and uranium with its daughter products. In the section of primordial radionuclides, the important part is the external exposure and inhalation exposure. In external exposure, there is a gamma radiation from uranium, thorium series, radionuclides, and potassium. And if we are going to the inhalation exposure, we can see here the radon and thoron, which emanates from the soil matrix and release alpha particles or alpha radiation. Now these are my study area, Nainital district and Almora district. As we know, the Nainital district is the coldest district in the India and is always the part of the attraction of for the tourist. This Nainital district, the important thing in this study area is this area is surrounded by the MBT region. This is the main boundary thrust and volcanic region, and the third one is the neotectonic activities or this is the important part of this study area, Nainital and Almora district. We can see here. This is the map of Uttarakhand, and it is showing the Nainital district. And we have collected some soil samples in this district because the geological conditions are very interesting in Nainital district. And the second one is Almora district. It has very interesting geological condition because of the MBT region. And this is the experimental methodology, gamma ray spectroscopy. We have used the HPG detector to find out the radionuclides, radon, thoron, and potassium, as used for the analysis of natural potassium. HPG detector based on high resolution gamma spectroscopy system, and after that, the activity of sample is counted. The efficiency for the system is carried out sources of uranium as it is easily available in any center. And after that, high quality generated detector has better energy resolution. These are the formula to find out the radium equivalent activity index. As we know, the radium activity and potassium activity. About the radium equivalent activity index, it is used for a standard index, and it is a single index to gamma output for the different radionuclides in a material. If we have the data of this radium activity, thorium activity, and potassium activity, we can calculate the radium equivalent activity index, and we can compare it with different radionuclides. Now, the external and internal health hazard index. These are the conversion factors. We can calculate the external health hazard and internal health hazard. Now, knowing about the radium activity, thorium activity, and potassium activity, we can calculate the absorbed dose rate G with different conversion factors. Now about the annual effective dose, if we have this absorbed dose rate, we can calculate the annual effective dose for indoor and outdoor with the help of this conversion factor 0.7. This is a conversion factor which converts absorbed rate into the human effective dose, equivalent with the outdoor occupancy 0.2 or 20% and 0.8 or 80% for indoor. Now the result and discussion. Analysis of natural radionuclides in soil. We have collected 24 samples in Almora district and 26 samples in Nainital district. These samples are collected from the area where the MBT region is passing through the area, the volcanic region, and the neotectonic activities present in that area. Or we are getting a high concentration of radon and thoron in this area. We have collected soil sample from these regions. We can see here clearly we are getting the variation in the radium 37 to 91 becquerel per kg, which is and the average value is the 48. But it is a higher value from the world average value, which is 50 becquerel per kg. The same we are getting a higher value radium, thorium, and potassium because of the interesting geological condition in Nainital and Almora district. Now this is the frequency distribution of the tabular of the tabular data. We can see here. This is the frequency distribution, and most of the data is shifting towards the lower concentration. In the case of radium, thorium, potassium, and radium equivalent concentration. This data is for Almora region, and this representation for the Nainital region. In this region, we are
लास्ट नाइट कर देना
okay.
कर देना
Okay. Now we can see here this log normal plot. It is shifting towards the negative skewed, and in this case, it is also shifting negative skewed distribution. But for the case of Nainital region, it is just we are getting a normal distribution. Now this is the representation for the health hazard and annual effective dose in millisieverts. This is the statistical representation for. Now it's a box crystal plot to understand the radionuclides present in soil samples collected from the Almora and Nainital districts. Conclusion, as I have discussed already, the average value of radium, thorium, potassium. Radium, thorium, we are getting a slightly high above the world average value, 50 becquerel per kg and 10 to 50 becquerel per kg respectively. The average value of potassium in the study area above in the limit is 100 to 700 becquerel per kg. Now the average radium equivalent activity was found to be lower than the recommended value, 370 becquerel per kg. The absorbed doses received were higher than the world average value, while annual doses received was under the recommendation value, and the internal and external health hazard indices and gamma index were below the recommended level of 1. So the purpose of this study can be used for the calculation of emanation rate in these regions, and it is important parameter in modeling radon level in the soil sample as well as in the outdoor and indoor air. The study will be helpful in bridging the source term, contributing factor, and the concentration value of the study area, important for future research. I would like to thank for BRNS for providing the funds in the form of research project. I would like thanks to Professor Amula sir, Professor Kuldeep sir, and Professor Hussain sir, always guiding me throughout my research work. References used during this presentation. Thank you.
Thank you, Dr. Kumar. Now, paper is open for discussion. Any question from audience? No question. Thank you, Dr. Kumar.